Hope you had a refreshing Easter break. Today we continue with our track on deep learning. We already spoke about the fundamentals, as well as applying deep learning techniques on images, and today we'll get started on moving towards text-based data. You have also seen, speaking of text-based data, that assignment number 3 has been made available as well. So hopefully the instructions for that are clear. Otherwise, let me know during the break or after the course. And also, as this slides deck progresses, we also get through some pointers on tools and other things that you might be willing to utilize for assignment number 3 as well. A little bit of news articles, not that much this time around. This I thought was pretty interesting. This is a new technique applied on diffusion language models. If you remember, already a couple of times in the news we said that the majority of language models, as you'll also see it actually in the chapter that we'll discuss today, the majority of language models make use of what's called a transformer-based architecture. But like was already mentioned, as we saw for images, diffusion-style models, where you basically train a model to take away or start from a noisy vector and basically denoise that to output some desired text, has also been experimented with. Now, up until so far, although the inference of those models is typically more performant than the transformer architecture, meaning that they're faster at generating their text, typically the quality is not so good. And this is a new article that claims that they have been able to take this diffusion style of language modeling and make it better. And basically the key kind of breakthrough or the key component lies in a different type of loss function that they have been applying. So basically you can go through the abstract if you're interested. And basically they say, well, we add in introspective consistency. So they claim that autoregressive models, AR models, that they agree with what they generate, whereas the diffusion language models often do not. And that's where they implement a new kind of loss piece, let's say, not a complete replacement of the existing loss function, but they add in a new piece to make that behave a little bit better. And they claim that they get good results. So maybe, who knows, in a couple of months, maybe that this style of architecture will also become more popular for language modeling. This is another paper which is also comes with a little bit of a weird result. A couple of years ago, we had like doomsayers saying that it's not a good idea for these AI models to roam free on the internet and to just generate all sorts of text. Because what was claimed at the time is people believed that if you overwhelm the internet with AI-generated slop, basically, that you would fall into some kind of model collapse, where if you then take that generated content and use it to train a new generation of your language model, that progressively your language models would become worse and worse if you try to train them on what they themselves have generated. And here the authors find that, well, the opposite is true, or they claim the opposite. They find that you can utilize what they call self-distillation and can utilize to continue to fine-tune a model. So they take an existing language model, they have it generate text, they sample solutions, so they sample generated text from that model with certain temperature settings, truncation settings, and then they continue to fine-tune on those sampled pieces of generated text. And they claim that this can be utilized to improve or to continue to fine-tune a model to have it work better on the text that it is generating itself. A very interesting paper, goes to show that some of the things that people believed a year or so ago, that maybe nowadays these things have already changed as well. Anthropic has been busy. Not only have they been announcing Opus 4.7, which is, again, a step forward in terms of being better at everything that it does. It's also a bit more costly, as is always the case with Anthropic. But you might have heard that they have also been experimenting with an internal model, an enormous language model that they call Mythos, and they have been afraid to release that because they claim that this Mythos language model that they have going on, that it was able to find all sorts of security vulnerabilities in existing software. So they said, we're not going to release that. This makes it way too easy for hackers to break into systems. We'll first contact software vendors, companies like Microsoft, Apple, and so on, to make sure that they can patch all of these holes first, or to make sure that we figure out a way to release this thing if we want to release it. Now, of course, part of that is also a bit of marketing. If you are an AI lab and you say that your model is so powerful that it can break in everything and you're afraid to release it, it's good PR, obviously, as well. But 4.7 has also been released, does a pretty good job, as is always the case. And also here, actually, in fact, the version of Cloud Code that was released has also been already capable to find security vulnerabilities in popular software packages. Things such as the Linux kernel, for instance, found a bug in the code there that could be exploited, and that has already been sitting there for 23 years. So it is indeed, or we can indeed see that as these language models improve, that they do become more capable at finding security leaks or security issues. And that makes them dangerous to a certain extent, obviously. So that's going to increase as we go forward in the coming months as well. And this is a bit of a fun article. This author takes a look at OpenClaw and says, well, I'm an old hat, an old grandpa in the tech space, and you can't fool me. I remember the bad days of MS-DOS, and so I've been taking a look at this OpenClaw thing, and I see basically, well, not really security holes, but kind of misconfigurations and things that can lead to issues down the line. So the author basically makes the claim why he won't be installing OpenClaw on one of his machines. So there's still a bit of a back and forth. Some people go completely wild with it. NVIDIA has been trying to make this whole claw situation a bit more secure, let's say, and a bit more sandboxed. But you also have people that are heavily against utilizing autonomous agents such as this one because they think that the risks outweigh the benefits, let's say. Okido. So then we can get started with our piece on text and recurrency. So what we'll talk about is, as you could say is always the case, we start a bit from the basics of text. It's not a text mining course. We do want to heavily or quickly go towards the deep learning approach on dealing with text, or let's say the modern approach of dealing with text. But we will take a look at some, well, if you can't use a deep learning model and all that you have is your traditional supervised learner, how could you still perform some sort of basic text featureization? Or in other words, what did people do before these deep learning models entered the scene in terms of you being capable to tackle text-based data that way? And then from there, we will move onwards to talk about what representational learning is. We'll talk about word embeddings, and from there, we'll switch to the recurrent neural network architecture, and then we'll introduce those transformers. We've been talking quite a lot already about representational learning. I've stated already in many cases that what a network tries to do, especially as you make it deeper, is its intelligence there is on the one hand about compression of information, and we saw that heavily when we spoke about the autoencoders, for instance, where your input instances were compressed down to a short numerical vector. And on the other hand, it's heavily linked to that. If you're better at compressing certain types of data, you're also learning to find good representations of that data. And already in the image domain, we saw, well, an autoencoder tries to find a representation from which you can reconstruct the original as well as possible. And when we were talking about these generative adversarial networks and things such as diffusion models for images and the variational autoencoder, we also said, well, there we sample from some noisy latent space, and from there the network tries to build up an internal representation to all the way down at the end, then generate the final image from. So a lot of the things that we do based on data and training these things boil down to we want to find good representations. So it's not only in text that this shows up. In fact, we have already seen it many times. But if you look historically, this concept of what is an embedding and what is a representation, traditionally or historically speaking, this popped up first in the domain of text. So it's a bit weird that we first went through images and then text, but that's how the structure is in our case. But this is not something solely unique to text. You can say that whenever you're dealing with some sort of deep neural network, it's trying to construct representations. And that is nothing less or more than a numerical vector, basically, from where it can then maybe separate some classes, maybe generate an image, maybe find a good representation for a piece of text, as will be the case today for us. So let's take a look. Well, why text? It's pretty important. Well, we do have a lot of images on the internet, but if you look at the traditional organization, yeah, if you get lucky and they already have some sort of tabular data source, some relational database, which is often the case, you typically have a good starting point to start applying your supervised learning techniques on those. But if you look in a typical organization, the majority of data that's lying around is of a more unstructured format, is of a textual format. And you see many examples there, but if you look at legislation, for instance, or even emails or social media posts and so on, a lot of the data that we have in the world is textual in nature. That's a bit annoying, of course, because that is unstructured, so we don't have a nice feature vector representation for text that we want to deal with. Unstructured, well, it's not fully unstructured, it's more or less semi-structured, I would say. I already mentioned that I don't really like the terms unstructured data because, well, text also has structure, right? Text has grammar, you have sentences, you have words, you have paragraphs, you have punctuation, and so on. But still, we are not quite yet at the numerical feature vector representation that we might want to get out of that. And moreover, text typically, it's meant between communication between people, so text typically is also dirty, meaning there might be spelling mistakes, or there might be ambiguous meanings, or double negations, or maybe sarcasm in text that you're dealing with, and so on. If you look at assignment 3 and you look at the reviews, for instance, of games, sometimes they are written in a humorous way, and then makes it pretty hard to deal with this data set. So we do need something clever to be able to tackle this. And as I already mentioned, just as with computer vision, also here you can make a clear, or you can see a clear split before deep learning was there and after deep learning entered the scene. So before deep learning arrived, you had people talked about natural language parsing and entity extraction and topic modeling and techniques such as LDA and so on. And all of that basically has changed or has changed after deep learning models entered the scene, which also here in this area have now become the majority case of tool that people apply on this sort of data. So if we are faced with some text and we do want to featureize it, how would we be able to tackle that? So we have a collection of, well, let's say documents, for instance, and each document in our corpus is a sequence of words. Later we'll also call it a sequence of tokens, a sequence of characters, but that's basically what our instances now consist of. So that's our corpus. The plural of corpus, by the way, is corpora, not corpuses. Each document then has tokens or terms. Again, it depends a bit on what we consider to be our vocabulary to denote what these tokens are. We could say, well, every word is a token, or every character is a token, or we're going to split up words into subsequences of 2 to 3 characters, for instance. That's what the majority of language models do nowadays. But basically, our vocabulary defines the tokens, the words that can appear in our sequences of text. Now, typically, in most cases, when you have a data set like a corpus, we will consider every instance to be a document. A document can be something like, it depends on what you're working with, but like a claim, but it might just be as well like a tweet, for instance. So you have your instances or pieces of text or documents in this case. And then we want to, again, we have those instances, and then the idea will be that we want to, maybe we'll also have a label, and we have maybe the sentiment of the review, and we would like to build a supervised model that, given a piece of text, can tell me what the sentiment of that review is. Is it positive, is it negative, is it neutral, and so on. So again, what you might want to set out is, I can't just directly give that to my XGBoost. What I'm going to do is I need to come up with a way to convert those documents, those pieces of text, to a feature vector, a real valued, as always, feature vector. And again, there you could say, well, if you take a basic featureization approach or a manual featureization approach, then it is you trying to come up with a good representation, right? All the way back in week number 2, when we spoke about pre-processing, and we saw those dummy variables, for instance. I also told you then that, well, basically this is just a representation that you have manually come up with to represent categorical levels of a variable. Not necessarily the best one. In some cases, well, it's a simple one, but it didn't also make the best use of the dimensional space that you have. Only one of the numbers was 1 there, and all the others were 0. Well, same thing here. Now we have a piece of text, and we also are wondering how can we come up with a feature vector, a vector representation for that piece of text. And of course, there are so simple ideas that you might come up with. For instance, you could say, well, I'm going to take my vocabulary that I construct. For instance, here I have 2 examples of short text sentences. The first is, this is an example, this is a second example. And for me, I will say, well, my vocabulary, for instance, will be words. So these are all the possible tokens or words that can show up in a piece of text. Either this, is, an, a, example, or second. And maybe I will also say already, well, to make my life easier, I might say if I have punctuation in there, I'm going to throw that out, for instance. And probably what I will also do is I will say I'm not going to make a difference between uppercase and lowercase. I'm perhaps first going to convert my text in a full lowercase format, and that's what I build my vocabulary upon. And then I can say, okay, if I now have a document, I do something like, well, basically I'm counting or I'm indicating now which word appears or which token appears in which document. So it's a simple binary representation in this case, set to 1 if the word appears in the document and set to 0 if the word does not appear in the document. So this is called bag of words. So now I'm representing every document as a bag of words, which is just a binary vector representation in this case. Easy, but not the smartest choice, obviously. We can do a little bit better. Like one thing which is a little bit, let's say, not so elegant, is the fact that I have a lot of stop words in there, things like an and a, that perhaps are not necessary to consider as a feature in this representation that I'm constructing there. So very likely I will also do some stop word removal and things like that. It's also quite crude because if I do it this way, yeah, I can order these feature columns in a certain way, but I lose a lot of the structure that was there in my text by approaching it in this manner. I lose the grammar, I lose the structure, and so on. And I lose the order of the words as they appeared in the original text. And on top of that, but that can probably be fixed quite easily, but you will also say, well, it's a binary representation. It's enough that a word appears once in a piece of text, but shouldn't you basically count how much that it appears? So indeed, that's something that we could also do to make this a little bit more refined. But even though this is easy to generate very quickly on larger pieces of text, if your vocabulary grows, you can easily see that this will also lead to an explosion of features, because the more tokens that you get in your vocabulary, the more columns that you add here in this representation. But this is simple, can work in simple cases if you apply careful filtering, if you remove stop words and so on. Now this is an approach that can work. Now, what you will have to do, as already mentioned, is very likely you will normalize in some way. So you will get rid of uppercase characters and you will convert everything to lowercase to reduce the number of, or the length of that vector that you're creating. So to reduce the number of dimensions that you're getting. What you also typically will find is that you stem words to a certain extent. So whether the word jump appears in your text or jumps or jumped or jumping, that you all map them to the same token in your feature vector, so that they all become jump, basically, so that you do not create 4 different features or columns for these 4 variants, but you only have 1 of those. And that can also help you to reduce the dimensionality of those representations that you're creating. So you can do that either by applying it directly on your source text, but basically it's a mapping that you do on the tokens that you have in your vocabulary. Depends on the language, obviously. So there is a simple algorithm called Porter's stemming, which works pretty well for English text. But you also have more complex techniques and very often also some sort of thesaurus-based or vocabulary-based, so that they also understand that better, good, flies, flight, fly, that these also belong to kind of the same thing. So a bit more advanced than simple suffix removal. You can find packages that can help you with that for different languages, but again, some languages are a bit special and might be less suited to doing something like this. And again, this is meant to take out dimensions of that vector that you're creating, but you're also throwing away some information, obviously, because jumping and jumped is not exactly the same, right? So it's a filtering that we apply to reduce the number of dimensions, but again, it comes at the cost of losing some context and losing some information. And then, typically, what you will also do, as already mentioned, is you download a list of stop words and you remove all of those as well. You don't consider them to be part of your vocabulary. No one is interested to know the fact that the word the, and, of, on, and so on, that these appear in a piece of text that you have. And then this bag of words approach can be quite workable if you set it up in this way. Now, I already mentioned binary vector, we can do a little bit better. Well, the next step then is, instead of just saying this token appears or this word, this term appears in this document, yes, no, they will also count the number of times that it appears. So then we're counting word frequencies. This is, of course, nice because then we can also make a differentiation whether a word shows up more or less in certain pieces of text that we have. And then typically this is called a document term matrix. Now, if you do that directly, We know from other cases as well, so these ones here would become counts, so maybe, well, here every word appears only once, but maybe you have a third example where example appears twice, for instance, so then you're putting counts in there. Typically, like with every feature vector, it's good to apply some normalization on top of this so that everything falls nicely between, let's say, 0 and 1. So typically what is done is dividing all of your columns by the total number of words that are in the document. And that's nice because then the impact of if there is a lot of variance in your instances that you have in your corpus, where some documents might be much longer than other documents, well, obviously the longer documents are going to weight heavier if you would not normalize in any way, because just because the document is longer will cause that words appear more often in that document. If you want to normalize it out, you can divide by the total number of words in the document. So then you make it relative to the length of the document. Or you can normalize by frequency of a specific term in the whole corpus, and so on. And also here, we have mentioned it already before a couple of times, but still here we do need to be a little bit careful, because once our model is trained, if we would utilize this approach, we would also have to think about, well, what if in inference suddenly there is a document that shows up and words appear in that document that I did not have in my training data at all, right? Well, again, same story as our whole pre-processing. First split your data set first, same thing here. Once your vocabulary is constructed based on the training data, you continue to apply that vocabulary on test instances as well. And so if a new word or token shows up that you didn't see in your training data, you also do not add it to your vector that you're creating here. But again, it is, of course, a signal, if that would appear more and more often, that perhaps it is time to retrain your model, obviously, right? Because if new words would suddenly start popping up all over the place and you're basically throwing them away, probably your model is going to suffer from that as well. Now, this already takes a bit into account that documents can be of different lengths, so that's not too bad. We have already tackled that. But something else that we would find is, even when we count words, and even after we have removed stop words, you can think, well, about, let's say you have a data set of legislation, of laws that you're working with. You might basically find that some words, they show up quite often, but that is not sufficient to say that these are really important features. Because if you have a certain word, like law, let's say, and it shows up in every document that you have, and it shows up a lot of times in every document that you have, it's still not very informative to then give that to a model. So just saying that something occurs often is perhaps also not sufficient. And what we would like to find is not only say, this word shows up very often, so it must be an important word to utilize. Also, we should be able to look across the whole corpus. If there is only a couple of documents where a word shows up more often, but not in the other documents, then that typically is a more informative token or term to utilize. So we would like to differentiate based on that as well. And something that can help us to do so is called TF-IDF. And that's a very well-known, very often used featureization strategy, or representation, you could say, strategy. Also manual, based on the training data that you have, but still works, or works surprisingly well. And the idea is as follows. Well, term frequency, that we already have, basically. That's the thing that we just calculated before. We just calculate for each term that we have in our vocabulary. So for each token that we have, or for each word that we have, we just calculate the number of times that that term appears in this specific document. And then we normalize, as we said before, by the length of the document as well. So that's basically the step that we did previously. But then we say, well, also, it's not just important that this word shows up more or less in this specific document that we're looking at. I just mentioned what is also important is this a word that appears at the same rate over all of my documents, or is there also some difference there? If this is the only document that this term shows up in, well, it's still an important term because it can help me to differentiate. Or if it only shows up in this particular document, even if it's only 3 times, right, might still be an important term. So the frequency in the corpus also plays a role, meaning that words or terms should, on the one hand, not be too rare, but we also don't want them to be too common. So we need a measure of sparseness of this term. And that's called the inverse, because we flip it around, the inverse document frequency. For that, we only need to do it or calculate it for each term, so for each word that we have. and basically it takes a logarithm of the length of your corpus divided by for each for each document in your corpus, whether that term shows up in that document. So you count over the number of documents, basically. You check in how many documents over the whole corpus does this term show up in. And basically the graph looks like this. And basically, the fewer the number of documents that contains this term that we're checking, the more important the term will become. And at the end, what we do with both of these pieces is we just multiply them together. So what we get is now, basically, you create two tables, document 1, document 2, document 3, and so on. And these are all your terms, so words like law and legal and so on. And the TF-IDF part, for that, you basically need to check it across all of your terms and across all of your documents, right? That's what the top formula says, because you're basically counting, well, how many times does law show up in document 1, in document 2, in document 3, and so on. So that's the TF part. And we normalize it based on the length of each document, right? Then, for the IDF part, basically for that, we only need, that's basically a single vector, because there, the IDF number, we calculate per term, but across the whole corpus that we have. So there, it doesn't matter later on if you multiply these two together at which particular document that you're looking at, right? You basically do that across the whole corpus. And then basically, by multiplying this part and this part together, you get your TF-IDF values. So let's think a little bit about this. So we do this on training data that we have. So again, your vocabulary needs to be settled. You need to decide what your tokens or words in this case are that you want to calculate the TF-IDF values for. Next up, let's say that it is finished. You multiply them. So the result will be that every document now is represented as a vector where you have multiplied TF times IDF for each term that you have. So the length of this representation of this TF-IDF vector is the same length as your vocabulary is, right? So the number of tokens that you put in your vocabulary decides the length of the representation that you're building here. So in this sense, still here, your representation, it's not, the length of that is not something that you can freely choose. The representation is dependent on the size of the vocabulary that you have built up. So based on how you constructed your tokens, how you did your stemming and so on, whether you did lowercase normalization, etc. Now, let's say then tomorrow you have a new document that comes in and you also want to calculate the TF-IDF vector for this new document. So now this was my train set. Now I have a document in my test set, document test, and I want to do the same thing. I've trained my model on this complete feature matrix that I have there, and now I want to test it out on a new document that I have. How do I do this? Well, for the TF part, I can apply the same strategy. I know my vocabulary, so that doesn't change. So I still have law, legal, and so on. And I also, again, just count the number of times that this term appears in this test document, right? I'm not doing data leakage. I'm just applying the same strategy there, right? It can be done per document, right? So also for this test document, I again calculate the exact same thing. And I divide also by the length of this test document that I have. So I just reapply the same formula there. But to multiply with the IDF values, there I use my learned numbers as I got them from my training data, obviously, right? So these become part of the model, so to speak. Those are parameters or weights of the model. So actually the IDF values, because this is something that you learn over more than one instance, as the formula shows, to calculate IDF values, you need to do this over the full training corpus, right? So once you have extracted and learned those values, you do reuse them and reapply them on test documents that come in, right? So again, that same story of doing everything first, splitting your data set first into train and test, and then making sure that you can apply all your featureization steps afterwards as well. So same here for IDF. And then basically also for test documents, you can construct a feature vector for those as well in the same way. And then you give that to Random Forest or to XGBoost with your label, and basically, typically, TF-IDF values will do a relatively good job. For larger documents, what might happen, even if you do apply lowercasing and you do apply stemming and so on, is that still it might happen that the representational vectors that you end up with, that they might still be very large, right? There are a lot of words in the English language. It could be quite easy to end up with vectors describing each document with TF-IDF values, where you have 10,000 different terms in your vocabulary. So then you will have a vector of length 10,000. So what most packages will also allow you to do is to say, well, vectors with a size of 10,000, if you only have 500 documents, your random forest is not going to work too well on that. So basically also to cut off the number of terms and to kick out those columns for which, for instance, the TF-IDF values are too low, or to only keep the top n appearing words or something like that. Depending on the package, they offer you different choices, but typically you will also have to kick out some of the features there, so reduce the size of that vocabulary. So you get a vector of weights per document in a manual way in this case, right? But that is then our representation and very often is used as a basic featureization technique for text documents. It also is used for other retrieval and representation tasks. For instance, if you would like to check how similar two documents are to one another, you could basically calculate something like cosine similarity between these vectors as well, right? And if you want to see, well, I have a query from the user and I would like to fetch out which document is most similar or most nearby this query that the user has typed in, well, I can apply cosine similarity on these TF-IDF vectors that I now have for each document. That's one representation. Maybe there are also better representations that we could come up with and where the cosine similarities would make even more sense, right? So this is just one way to represent our documents as a feature vector. Later we'll see how, with deep learning techniques, how we can learn those representations from data. Here we basically apply a formula. We also learn it because we do learn these IDF values, but it's not really a very powerful text-aware kind of representation technique that we have yet. So this is an example showing that off, for instance. So what was done in this example is you take 15 jazz musicians, you take their Wikipedia page, which is basically text, you apply TF-IDF to convert each Wikipedia page to a TF-IDF vector. So now every page is represented by a vector. And then you let the user type in something like famous jazz saxophonist born in Kansas who played bebop and Latin. You also take that sentence. You also convert that into a TF-IDF vector using the learned IDF values that you have. And then basically you try or you apply cosine similarity between the query that the user has typed in and all those Wikipedia pages that you have with those TF-IDF vectors. And you hope that the musician, which is here Charlie Parker, seems to be the most similar one to the query that you have typed in. So that can be utilized as a simple retrieval setup as well in this case. And again, it doesn't really matter later on if you use TF-IDF vectors to represent your text or some other embedding technique. You could apply the same strategy. As long as you have vectors for your text, you can calculate similarity between them. Another prominent approach, which is an alternative to TF-IDF, is called BM25 or Okapi BM25, and BM stands for best matching, and 25 relates to the configuration of its parameters. And it's more or less a little bit similar to TF-IDF. It gets utilized a bit more also in information retrieval tasks. But basically, it also uses IDF values. So for each term, as we see here, this is called Q in this case instead of T. And we also calculate frequencies as we did in the TF-IDF formula. But you see that now they're weighted in a specific manner. It also uses the average document length to normalize in this step. And then this K1 and this B, those are three parameters that you can pick. And typical ranges are 1.2 or 2 for K1, and B is typically set to 0.75 by default. Same as TF-IDF, except that the formula is a little bit different or a little bit more complicated. But at the end, instead of then having a TF-IDF vector for each document, you end up with a BM25 vector for each document. Also, this still commonly is used up until today. It's a simple technique to represent documents, and typically then if you apply cosine similarity on the vectors that you get here, they often don't do too badly. In some cases can even outperform more complicated embedding models that do use deep learning. If your task is relatively simple, this is not too bad of an approach. So also here, basically, we can then calculate this for each term separately. So this original formula assumes, that's why it says Q here, that it works with a user query, right? And that's sometimes why it's not immediately apparent, like why this could be utilized instead of TF-IDF, because what if I just have a bunch of documents? I do not have a query yet. I just want to represent the documents that I have. Basically, just by rewriting it a little bit, you can also say, okay, I have a weight for each term in my vocabulary. So here this TI pops up again in a specific document that I have. And it gets calculated also as a multiplication between the IDF value, which is specific for a term across the whole corpus. So again, you need a piece of training data for that, but now not multiplied by the term frequency, but still by this thing. So the reason why this works a little bit better is because in this part obviously doesn't change anything to the IDF part, so that's the same as in TF-IDF, but the TF part, the thing that it adds here, helps to saturate the term frequency. And what that means is that repeating a word 100 times, for instance, does not mean that it's 100 times more important, so it flattens out a bit this term frequency, or the effect of that frequency, a bit better than, or better than standard TF-IDF does. And also the way how it normalizes using the average document length also makes that this works a little bit better. So you can call this a bit more of an advanced version of TF-IDF, but also very often used. Now also, if you do this, again, your feature vector will be of a length that's given by the size of your vocabulary. So you will have to, in many cases, also here, apply some sort of feature selection. So you only keep the most frequent words, or you try to kick out values of your TF-IDF values for terms that do not change a lot, things like that. So you apply standard dimensionality reduction techniques on top of that as well. You can also do something like t-SNE or UMAP, as we saw from the unsupervised learning course, to maybe try to reduce the dimensionality of this, but then your resulting feature vectors will be less understandable, right? In the original, every feature that you have in that vector corresponds with a particular term. You will lose it if you try to squish or dimensionality reduce it with a technique like t-SNE or UMAP, but that's also something that you can do. Or in pre-processing, you might refer back to the hashing trick that we saw, where we also try to collapse the number of dimensions that we have to n hashed features. And that's, let's say, the standard approach. If you have text and you have a label and you would like to apply some sort of supervised learning, then this is what you end up with. And typically, if your texts are not incredibly complicated and your labels are relatively easy to predict, then TF-IDF or BM25 will normally do a good job. Now, we can then try to extend this a bit and introduce a bit more questions or complexity. So for all of what we did with that token vocabulary that we have, it basically threw away the order of words, right? I select here a certain ordering of my features and I say that law is my first feature and then legal, but it doesn't matter, right? There is no ordering in this feature matrix that retains the original ordering in my documents. I could swap these columns around and to my random forest it wouldn't matter, obviously, right? A model or a supervised learner does not care in which order that you order your features in. However, we do know that in the original text that we have, that order between words can be important, right? If you say not happy, right, that's something different than the fact that the word not comes way later after the word happy, right? So if you negate something, it might be a good idea to say, well, I would like to keep these two words together somehow, right? Because not happy is not the same as happy showing up. It means that you're unhappy, right? So how can I also retain a bit of word order in there? And a first solution or a simple solution would be, well, I have freedom to decide what's in my vocabulary. So instead of also putting in single tokens or single words in the examples as we have been seeing them so far, I can also look at pairs of words and make those part of my vocabulary as well, just as any other term. And in that case, in your TF-IDF feature, you might calculate a value for not. You might calculate one for happy in a particular document, but you might also say, well, if those two appear directly next to each other, that's just another term, just another token that I'm adding here to my vocabulary. And I'm also going to retain all of those combinations as well. Now, that's called an n-gram sequence. So a bigram is a combination of two words, and you make that part of your vocabulary. You can see the issue, however, is that if you do it this way, your dimensionality will completely explode. It wasn't that good to begin with. If now you start applying this, it's going to completely get blown out of proportion. Let alone that you would like to do something like trigrams, where you use triplets of terms and you add those in your vocabulary as well. That's not really going to work anymore. So this greatly increases the size of your feature set. So might seem like an idea, but typically you can't go much further than bigrams, and typically you would also be selective on the ones that you retain in your vocabulary. Maybe only those where they start with the word not and then something else, for instance, or maybe some selections like that. Otherwise, your dimensions will explode even further. Another thing that you might beacon now that we're talking about ordering, yeah, same thing for grammar, obviously, trying to extract a bit of a richer structure from text. Like I said before, the era of deep learning, that was then what brought you to natural language processing techniques, where people try to come up with techniques where you can make a better difference if you have two reviews, and one review is for a camera and says this camera sucks, and another review is for a vacuum cleaner and this vacuum cleaner really sucks. Yeah, how can we understand that maybe in this case this is a positive remark for the vacuum cleaner, and in this case it's a negative remark for the camera, right? How can we better deal with negations? How can we better deal with sarcasm and things like that? These are harder to retain or to capture in these simplistic representations that we're building up so far. So in this space, the best known tasks or techniques, algorithms that were out there that you could apply are things such as part of speech tagging, where you can have a model indicate which verbs or which tokens rather in a piece of text correspond with a noun, a verb, a subject, and so on. So to understand the grammatical structure of a text a bit better. Named entity recognition means that you apply an algorithm and you have it extract names of companies, names of people, dates, financial numbers, so to extract in a bit of a structured way specific pieces of information. And another one is topic modeling, where you say, well, I would like to represent each document that I have as a mixture of topics, and the topics have to be learned automatically by this algorithm. And then I can say, well, this first document is 80% topic 1, 10% topic 2, 5% topic 3, and 5% topic 4. And then by looking at these documents, you can then maybe say, topic 1, if that shows up often in my documents, that seems to be a sports topic, for instance. And then you basically have a linear combination of these topics, of those weights, and use that to represent your documents with, as a mixture of these topics. Now, all of these techniques, you can see some examples here. So this is part of speech tagging. This is this named entity recognition, where you try to extract persons, where you try to extract dates, where you try to extract consumer goods, locations, events, and so on. Can be quite, or in many cases, if you deal with text and automated text processing, is quite an important task that you're capable to do this. So we had some specific models to help with this sort of thing. Nowadays, obviously, whenever you have a task like this, you basically know the answer, what people will utilize. You use a large language model for this, right? And you just ask an LLM, please extract me all the names and events and dates from this text and give it back to me in a structured JSON format, and you're finished, right? So the choice nowadays is not which algorithm am I going to use for this, basically don't bother, but should I use a local or a cloud LLM? Should I use a large one or a smaller one? So all of these, let's say, approaches have been replaced by LLM-driven text processing nowadays. So that's just the nature of the thing. So poor professors who are working in the field of NLP, but their life obviously changed heavily after the arrival of these large language models. This is an example illustrating topic modeling. This can still be quite interesting. So here the most well-known techniques are LDA and LSA, latent Dirichlet allocation and latent semantic analysis. And basically they use a probabilistic approach to then say, well, each document, as you can see here, can be represented as a mixture of topics. And also this is then a representation for a document. Now your representation is grounded in the fact that a document is basically composed of a mixture of documents. And again, this is another feature vector that you could then give to your standard XGBoost or whatever. And maybe you could even combine it with your TF-IDF features to make your representation a bit richer. So that can still be interesting. It might be a bit harder to give a bunch of text to an LLM and ask it, well, represent me this as a vector over different topics. Probably you would be able to do that as well. But I would say that out of the tasks, out of these 3 tasks, that topic modeling is still something that can find some value. What they will not do in the majority of cases is also give these topics a name, right? They will just say, well, you want 10 topics, okay? So they also give you, which is also nice, freedom in terms of how many topics that you want to retain. So you do have some influence here over the length of your representational vector. So let's say we take 10 topics, and basically the technique will say, okay, document 1 is 20% topic 1, 50% topic 2, 10% topic 3, and so on. Right? But then by looking at some documents where topic 1, for instance, is heavily represented, by a visual inspection, you can then typically see what the topic 1 tries to indicate. And you will go, this is mainly about business news documents, for instance. Or you could then try to cluster using k-means, for instance, and maybe giving some documents to an LLM and ask it, what do you think the common topic is across all of these documents, to help you give those feature columns a name, basically. So that's still something that you will have to do if you utilize these models. So okay, that's basically before the era of deep learning. What happened afterwards, or how this then basically started off with these new approaches. And in the textual domain, it started with a concept that that is called word embeddings, as, let's say, an automated way to learn representations rather than the manual way as we have been doing it so far. So we want, at the end, we would like to get a feature vector describing all of my documents, but I'm not going to do that manually. Can't I, given the data that I have, build something that builds me the best representation automatically for me? And the initial techniques that popped up there, it's a little bit weird, but originally, or the first techniques, they didn't do so to find representations for documents, but it started by finding representations for words instead. It's a bit annoying because typically if you work with a corpus of documents, your instances are documents, not individual words. So you can kind of think about, well, I do want a representation for each document rather than words. But nevertheless, we will see that it can reveal some interesting patterns and can help us to do a couple of things here. So for documents, you already saw bag of words, n-grams, TF-IDF, but we know the issues with this, or representation is still relatively sparse and also very high dimensional. So we could wonder, is this now the best representation that we can get? Even worse is that, let's say that I would, for instance, try to find representations for each word rather than for each document. You might still then think, if I would then have my standard way of working, I could still represent a document then as a sequence of such representations. I will just take the representation for each word, I will concatenate them together, and that's what my representation for the whole document then is. Yeah, except the fact that then your instances that you've built up, your representations, are now of varying length. And we know if you work with something like an XGBoost or even like an MLP, that on the input side, your number of features needs to be fixed, right? It can't easily work with something that has a varying size, right? Which is also later why we will introduce the recurrent neural network, because that will allow us to deal with inputs of varying size. But for now, this is also something that is still bothering us or not so easy. What you could do is, if I would give you a way to have a representation for each word, from there you want to build a representation for your complete document, you could average the vectors together, basically. You could just take the representation for each word and then just average those together, and you also get a fixed size representation. But then you will probably say, but if your documents are long and you average all of those vectors together, aren't you washing out information? But might also be a simple way out to deal with this thing. Now, nevertheless, let's say that we take a step backwards and we'll say, okay, let's start with words at least. We're going in an automated manner, going to build up representations for these words. What do I want from those representations? Well, they need to be meaningful, right? My embeddings, my placements, basically. So that's why it's called an embedding. I'm going to embed each of my original items, words in this case, but we can also apply embeddings in recommender systems. It's applied on items and users, for instance. In this case, it will be our words. Of a fixed set, we know the English vocabulary. We know the words that are in the English vocabulary. And for each word, I'm going to find a placement, an embedding in this vector space that I have of in this case, then very likely a length that I can choose as well. Like with my autoencoders, I could also choose the intermediate representational length by the number of neurons that I stuck in there. And what I would expect to see, or hopefully from, if I then have those embeddings or representations for each of my words, probably similarity in some way, that I can reason with those vectors, that I can maybe calculate with those vectors, and maybe that words that are very similar, that indeed they also end up very close to each other in that embedding space, right? Similar to as we saw with dimensionality reduction techniques, they also had some underlying concept like that as well, based on distances. So we're going to construct, again, a vector of numbers for each word. That's where we'll start from, in the case of a word embedding. Dense, so now we're not just going to give a dimensionality of 10,000 and only one of the numbers is equal to 1 and the others are close to 0. The dimensions that I do have, I want to utilize those as well as possible. Right? Typically, we will need to have sufficient number of dimensions, so probably with 2 or 3, that's not enough to represent all of the words that are in the English language. Typically, 512, 1024, something like that. So for every word, I'm going to find a position in that high dimensional space. So these vectors are basically coordinates, right, where every word gets placed in that embedding space, so I obtain a representation, and then I can use my favorite distance metric, at least that's what I expect to get at the end, to then reason with those words. So what is a good embedding? Well, I already said in the case of dimensionality reduction, a good embedding there, a good representation there, is probably one that allows you to reconstruct the original instance as well as possible. And that's exactly in the case of autoencoders what we had there. In the case where we were generating images with our variational autoencoders, there basically our embedding that we started from was this sample that we took from that latent space, from that noisy input space. Well, there we basically expected that a good embedding there was in such a way where maybe one area of my input space was for the white cats and the other area is for the black cats. So also there was depending on the task. Now for words, also there I could say, well, there's a good embedding there, right? And there are different things that you could come up with. It also depends a bit in terms of, do you already have some supervised task in mind that you might want to do, right? Maybe there, then a good representation is one that helps you to linearly separate those classes that you have. But let's say for a very general purpose approach, I do not have a specific supervised task in mind yet. I do have a lot of data. I can basically scrape or I can download the complete English Wikipedia and I can use that to make representations for each word that shows up in the English language. And so there, what would be a good representation be? Well, like I said, probably one that captures similarity in some way and maybe the intricate dimensions that are present in language. Maybe one dimension tells me something about how much of an animal are you. The other dimension tells me something about, are you more a person or are you not a person? Now, these 512 dimensions that I will have, it's not that they will exactly map to concepts like that, right? But ultimately, I do expect that by training and by learning on this data that I have, that my model, that my algorithm will utilize the dimensions that it has as effectively as possible. Okay. Even better would be that if I then take those coordinates, those vectors, that I could ask questions such as, that would be fantastic if this would work, man is to woman as king is to, and then I basically take, okay, what's the step that I need to take to go from man to woman? I then start from king and I take the same step, and then give me the words that show up around this zone that I ended up in. Ah, queen is nearby. Ah, indeed, man is to woman as king is to queen. And so maybe some of my dimensions would indicate male-female relationship, or maybe indicate the tense of a verb, or maybe would indicate the relationship between country and capital, right? Maybe not across the whole dimensional space, but maybe in some local pockets and so on. But this would be nice if we can reason with these vectors like that. And indeed, that's exactly what you see happening once you train a model on a whole bunch of English text, and you have it obtain vectors for each of these words, that you can indeed do similarity, reasoning, and analogy tasks like this. So that's nice. At least at the level of words, we can see that there is some structure, some richer structure that has been able, or that we have been able to capture inside of those vectors. So the question will be, how do we construct them then? How do we learn those embeddings? You can download a pre-trained set of vectors. You don't even have to do this yourself. Words in the English language, they're pretty stable, right? So once you have trained them once, at least you can reutilize them for other tasks as well, right? But basically, if you would like to start doing this yourself, what are approaches that you can take? So we have a whole bunch of text, and we need to come up with a task where in some way, so I'm going to set up probably an artificial neural network again, and I need to set up a task where somewhere in the middle, like with my autoencoder, I can extract a vector from it. So I can start with a word on the input side, and then somewhere in the middle I can extract a vector that I can utilize. But since I'm training this thing, I also need to give it a task. I do not have a specific supervised label yet, so I'm going to create one. And again, this is an example of a self-supervised task, meaning that I do not have a label at my disposal, but I'm going to create one. Like for images there, if the only thing that you have are images, we already saw examples, well, there we can basically set up some self-supervised task where maybe one model is trying to create fake images and the other model is trying to detect which one were the fakes and which one not. So for text, if you think about what are tasks that we can set up there to maybe learn the structure of language, well, I could say from this whole English Wikipedia that I have, I will take a random 5-gram, so 5 words that appear next to each other. And maybe sometimes I will also just generate a random 5-gram. And maybe the task could be that my model needs to learn, is it a real one or is it not a real one, for instance. So again, I'm trying to create something to have it differentiate between real text and text which is not real. Maybe that could be a task that I can come up with. That would work, or this would certainly be something that is not viable. But very often in text, the self-supervision task that we set up instead is, I give you some context, and you need to complete the context. Now, not yet, but later, when we switch more to language models, the way how we will set that up, or how we will train those models will be, I give you a fragment of a sentence, and you need to predict what follows afterwards. You need to complete the sentence, basically, right? We could do the same thing here as well. But for word embeddings, we make life a little bit easier because we're not really training this thing yet to be very generative in nature. So what the earliest approaches did is they give, again, a certain randomly sampled context of words. I am very happy today. And says, well, that's what you get as your context, the 2 words before and the 2 words after. And your job is to fill in the missing word in the middle. So your job is to predict very, for instance. So that's what these early techniques did. And then the more text that you have, the better. It's easy to set up these instances or to sample instances from a whole piece of text like that. So we're going to train a model where, given some context, it can complete or predict the focus word, the word in the middle. And we're going to train it in such a way where also at the end I can easily extract vectors for each of the original words that I have in my English vocabulary. You can do that with matrix factorization-based techniques, but neural networks are a bit more powerful to do that, so that's what we'll utilize. For documents, this will not be very perfect yet, but at least for words, the nice part is, like I said, that words do not change, so at least once I've trained this and I have the vectors, I can maybe utilize them for other tasks as well. Okay. So this approach that we're going to set up, where we will utilize a neural network to predict exactly this, is called word-to-vec, word-to-vector. Already a very old approach by now. So this was invented by Google in 2013, so that's already a lifetime ago, right? But basically introduced or kickstarted this switch from more traditional approaches, let's say, to neural network-based approaches. And also, interestingly enough, at least at this level, working at the term level or the word level, we will not even have to make our architecture very deep at all. So it's also a relatively shallow neural network that we will set up, as you will see. So the assumption in our training, you can see in a different example, is we're going to set up something where we give it context, the part in green, and we'll have it learn to predict the word in the middle, the focus word. So we're going to predict a word based on its context. And we can set this up in 2 ways, and the 2 ways are called continuous bag of words, or CBO, or continuous skipgram, CSG. And the difference lies in the fact that if you look at this example at the bottom, that actually you can go two ways. You can either say, I give you the context and you need to predict me the focus word. I could also say, I give you the focus word and you need to predict me the context. That's the opposite approach, but would also work. So we can start with SIBO. So here you can see the schematic of the neural network that we will set up. Basically 3 layers, so this is not really too difficult, and it works as follows. I'm going to draw it from the beginning, unless I have... I'm going to explain it by drawing, it will be a bit easier. I need to start with so I have a context and I have a word, in the case of SIBO, my focus word that I want to predict. And let's say in the beginning I'm going to make it easy. And I'm going to say my context is only one word, to start off simple. So maybe the word that comes before is my context, and you need to predict me the word that comes afterwards. So my input that I need to deliver to this network consists of a word. But yeah, I can't just give a word in my input layer, I need to represent that numerically some way. And there we take the easy way out. We just say, well, in this case, the input layer has as many neurons as the size of your vocabulary. So as the number of words that you have. And then to indicate which word is the context word, I just one-hot encode. So one of these neurons' activation value will be 1, and all the others will be set to 0. So that's just a simple dummy representation on the input layer. Then it looks more or less similar to kind of our standard autoencoder setup that we saw previously, in fact. My next layer consists of, let's say, n neurons, and I can choose how many there. So this will determine the size of my representational vector. So if you would like a representational vector consisting of 4 numbers, let me put in 4 neurons in here. And here, the connections between them, this is simply a dense layer that we have on top. So everything is connected to everything else. So the number of weights that I will have here is V times n weights. I'm not including bias weights, right? So I'm just doing V times n weights. Then, well, I'm not there yet. These are just 4 numbers that I get out of this, right? What do I need to predict? My focus words. So also my last layer will again be of size V, equal to the number of words that I have in my vocabulary. And so here I have n times V weights, also densely connected. And here I hope that my network, so probably this is just with a softmax on the top, right? So I get probabilities that my network predicts me the correct word, right? So if not is my input and happy is my expected one, well then I will compare this result with 1.0 if that corresponds to the position of the word happy in my vocabulary. And I use any sort of loss function that you would like to utilize, right? So just something like cross entropy, for instance. I would just train it as any other regular network. So very simple. It's just a standard MLP, basically. But you do feed it a lot of example pieces of text to train from. So this is the example for that one context word. So 4 units in the middle, weights V times n, and weights n times V. Once I've trained this thing, and I then would like to know what the representational vector is for all of the words that I have, there are basically 2 places that I can extract it from. I can either take the first weight matrix, which has V rows, so a row for every word in my vocabulary, consisting of n numbers. So those are my vectors. But I can also utilize, if I want to, actually here I have 2 options for me. I can also utilize this weight matrix as well. And typically, well, people use the first one, but using the second one is possible as well. So you basically get 2 sets of representations for free, or for the price of 1, let's say. In this case, this hidden layer also, because I'm using one context word, needs no special activation function. Right? So it's just a sum of products of the incoming things, so no special activation, no sigmoid or something like that, basically a linear activation. The final layer, however, yeah, there I do need a softmax, because these y's at the end, I want those to be probabilities. Right? So there I do have an activation function, namely softmax. But that's for one context word. Obviously, I'm not going to use a context, well, I could, but let's say I want to increase my context now a little bit and expand it a bit. So here you see the setting where I introduce more context words. Well, what changes? First of all, at the input layer, well, now if I want to give it 3 words instead of 1, or maybe let's say 4 words instead of 1, right? The 2 words before and the 2 words after my focus word, I do the same thing, right? Context word 1, context word 2, context word 3, and context word 4, and all one hot represented. Right? So now my input is not a vector, but is a matrix of a size C, the number of context words, times V. So now that is my input size. And now there is a trick that we will apply. And the trick is as follows. So you will note here in the figure that the weight matrix that we have here in the first layer, so here nothing changes, right? Once I have reduced this down to n dimensions and I then want to go to my output layer, this weight matrix is still n times v in that case. But here something special happens. You see that here the weight matrix is still of a size v times n. And you would expect, if we would densely connect this layer to all of the neurons in this layer, that now the weights that I need in here would be c times v times m. But the C is not there. Why is that? Well, because we apply weight sharing, meaning that we use the same bunch of V times N weights, and we apply them on all of the columns of my input. So I do not learn separate weights depending on the position of my context word. I multiply with the same weight matrix multiplication across my context dimension of my input. So basically, I apply W times V, or this weight matrix, on the first context word, on the second context word, and on the last context word. The same weight matrix. But we're not there yet. Even if I do that, if I apply this weight matrix on the first column, I have here V numbers, I apply this weight matrix, I get an output of size n, my 4 numbers. I apply it on the second column, I get another set of 4 numbers, I apply it on the third column, I get another set of 4 numbers, I apply it on the last column, I get another set of n numbers. So even if I apply weight sharing and I multiply in this manner, my output that I would get here would not be a vector of size m, but it's going to be a matrix of size c times m. And also that we don't see happening. We still see that the output there is just n dimensions, not c times m. Why is that? Because now, after having introduced more than one context word, this hidden layer in the middle also gets an activation function. And what it does as its final step to produce the output of that layer is to average across the context dimension. So we average so that my final output in this layer is still just an n-dimensional vector. So now, when you train this thing, again you have the choice at the end. Do you use the WV times n weights, or do you use the n times v? But again, now you have a representation for each word. So my input now looks something like this. My weights matrix, the first one, looks something like this. I get this as an output with 3 rows and n numbers per row, but I average the activations down. Right? And you could also say, well, you could utilize this as a representation, but basically once this weight matrix is trained, you have a vector for each of the different words in your vocabulary. So that's then your representational matrix. So after you have trained, this is just a one-hot lookup, basically, in a weight matrix. That is what an embedding is. Basically, and you can do that not just for words, but for items in general, if you have a fixed set of items, an embedding layer basically says, well, the input is going to be one-hot encoded. It says this is item number 3, for instance, and I need to map that to an n-dimensional set of numbers. I need to map each item to a vector by learning these weights, basically. So that is something that you can't only apply for words, but later on you can apply for categorical levels as well, for instance, or for movies in a recommender system dataset, or users, and so on. However, the key thing with this embedding versus other types of representation learning is that here the set of your items is assumed to be fixed and known beforehand. Right? Words in the English language doesn't really change. We have them, they're there. It's not that tomorrow there is a new word that's going to pop up. In other cases, like for instance for movies, for instance, if you say, well, I start with a vocabulary of 10,000 movies and I want to find a vector for each of them. Yeah, tomorrow I have a new movie that comes out. I can't magically add in a new row to this weight matrix and continue training my network in that case. So this is good if we know that our set of items is fixed and known. If I would like to have something a bit more parametrically driven, well, then maybe some type of autoencoder-based setup, which does not assume a fixed size, might be better suited. So that's specific here with this embedding layer, the fact that we basically have a vector for each item, and we know the set of items, words in this case. So now, yeah, we have the weights of the hidden layers from which we can obtain the word vectors after training. Yeah, we can apply division by the context size to normalize a bit, but that's not even necessary. So you could first divide that weight matrix by C, the size of your context. In this case, in the case of SIBO, we present the complete context on the input, and we have it predict the focus word, the desired focus word at the output layer. What you will note, however, is since we are applying weight sharing here, is that the ordering of the context does not matter, right? So if I would give it the example of, what was it? The example here. An efficient method for high-quality distributed vector, if that is my context, if I swap the ordering of that green part around, my model is going to give me exactly the same prediction, right? So it does not take into account the ordering of the context in this case. And why not? Well, if I swap columns here around, yeah, I'm going to apply the same weight matrix. The order here will also be swapped around, but since I'm averaging down, it doesn't matter at the end, right? So in the end, I get the exact same prediction. That's not really, like if you think about language, you will again say, yeah, but order does matter, right? So it's not perfect yet, but here we're trying to learn simple representations for words. Maybe it's sufficient that we do have the context. What the order of that context is, maybe doesn't matter so much in this case, or works well enough. But if we do want to have order taken into account, we would have to come up with a more intricate scheme. But this is SIBO. CSG then swaps it around and says, okay, we could also say that the focus word is the one that I give at the input layer. So now, again, one hot encoded, like before, but now my input starts with the focus word. And I would like to predict the full context based on that. So you could say, well, something that I could do is I first convert using the same setup with a V times N weight matrix to an N-dimensional hidden layer. And then again, I'm going to apply an N times V weight matrix to construct C times V, a C times V output matrix. And I'm also going to utilize weight sharing in the purple part there. Yeah, but wait a second. That doesn't work as straightforward as we might hope it to work, right? So the idea here is as follows. So this part, easy, I just do V times N to get my N-dimensional vector again. So that's now just a single vector. And then I have an N times V, and I decode off from there to get a C times V dimensional output. But the figure is, of course, not fully correct. It's kind of a representation of what we would like to happen, but we can't make it happen like this. Why not? Well, if I have a single focus word, and I have a bunch of weights, and I construct an N-dimensional representation with N activation values, and then I would apply weight sharing and utilize the same weight matrix to get 1, 2, 3 context words. These vectors will, of course, all be exactly the same vector. I have the same weight matrix that I'm applying on the same numbers. There will be no difference between those 3 vectors. So that wouldn't directly work as I would like it to work in this case. What you could do is you could say, oh yeah, but in that case, no weight sharing anymore, right? I'm just going then to utilize a n times v times c huge weight matrix here to decode the full context of that in one go without having to apply weight sharing. Yeah, but then your weight matrix, of course, would become very large, maybe would also train a little bit worse, and also then you're basically forcing this output part here to take ordering into account. In the first setup, we said, well, the ordering of the words in the context doesn't matter. Here, if you would do that, you will make it matter. So can't we just have something that works equivalently in that case? And indeed, we do need to then to simplify it a little bit. And what actually happens during training is that we do not expect this thing to predict the full context in one go, but we just give it pairs. And we say, okay, for the same focus word, and my context, this is my focus word. And let's say that my context is this, is my word. I'm going to construct from there 3 training examples, one where I give it the input focus and I will have it to predict is, one where I'll give it the word focus and I will have it predict my, and one where I will give it a focus word focus and I will have it predict word. So I just restructure the way how I give my training samples in this case, and I basically only ask it to predict a single context word as well, but I repeat that training multiple times. And you will say, yeah, but poor network, basically you're giving it conflicting information because sometimes you're giving it focus, but you expect to predict is, and then you expect to predict my, and then you expect to predict words. I mean, how could it ever get a zero loss in that case, right? It will always make some mistakes. Yeah, indeed. So the best that it can probably do over epochs of training is distribute the probability values across these words that show up at similar rates, right? The loss will not be perfectly zero, but that's the case for SIBO as well. Also in this case, I might have the exact same context, but with a different focus word, right? Also there, it will not be capable to get a perfectly zero train loss at the end. So that's expected. I don't want it to have a zero loss. I just wanted to get or learn good representations and come as close as possible. What I could also do to make this CSG approach work is I could also say I'm going to give both at the input layer, right? And I'm going to give, for instance, a one-hot encoding for the focus word. I'm going to give a one-hot encoding for is, so for a context word. And then I'm going to stick something on top where at the end it just needs to predict me a single probability, indicating does this context word show up together with this focus word, yes or no? In that case, of course, I would also have to mix in some examples where the answer is no, right? So here, yes, they show up together, yes, they show up together, yes, they show up together. Maybe I give it another example where I say focus and you need to predict, or the context is pizza, and you need to predict me 0. No, they do not show up together around each other. So then you could also utilize a binary classification style setup to reach or to set up the same thing. A bit less common than the first approaches where we just have it predict context words separately, but you could also set up something like that. So that's CSG. Same here, when we're done, we throw away the network, we just utilize this weight matrix to get our representations. The size of the hidden layer determines the word vector dimensionality, so very comparable to autoencoders as we already saw. And of course, to make it a little bit more, you can train this and you can set this up with a standard MLP as you saw it on the slides or as we have just described it. Obviously, there are a couple of tricks that you can apply, right? If you want to make this train even faster, the idea, for instance, is that maybe some words appear more often than others. So you don't need to retrain or completely train so heavily on those. You have already seen them enough. And maybe it's better that you focus a bit on the more infrequent words and do some more training on those examples instead, so that you also take the frequency of words into account to construct your training samples with. So that's a trick, or that's an extension that is typically applied in this case. What you will also note, since both the input side and the output side are one-hot encoded, if you look at how you would do your weight updates, basically, you can probably also make some improvements to change those weight matrices when you're doing stochastic gradient descent a bit more rapidly, because most of your inputs are 0 and most of your desired outputs are 0 as well, right? It's one-hot encoded, so you can maybe also implement a couple of speedups based on that. So typical dimensionality, something around 1,000. Now, 1,000 is not something that you can easily visualize, like on the figures on the right that you typically see. So very often, as an after step, you then do a PCA dimensionality reduction on those vectors, or you apply something like t-SNE or UMAP if you do want to visualize those word vectors. And then you will say, hey, but wait a second, if all we wanted was 2 dimensions to make a figure, why not set up our neural network to begin with only 2 dimensions in its hidden layer? Well, because maybe you also want to do other things than visualizing. Maybe you also would like to do some reasoning or analogy tasks. And then it's nice that in your original representation, you still have sufficient dimensions for the network to put as much information as it can in. Something very similar to Word2Vec is something called GloVe, Global Vectors Model for Word Representation. It is built upon the Word2Vec skipgram model, but it exploits word co-occurrence information a little bit better. It's a small improvement. The output is very similar, but that's also something that typically is mentioned in the same space as Word2Vec is. So this was going quite well for a while, but then obviously, if you're a social media platform like Facebook, and maybe you would like to use this approach to help you featureize posts that people are writing, we don't really have a solution yet to featureize a full document. We have vectors for each word, but like we said, what we could do if the posts are relatively short, we could take the vector for each of the words in that post, and we could average the vectors, and maybe that's not too bad of a representation for the post as a whole as well. And so Facebook was playing around with that and was experimenting with that, but what they found is that, well, already just trying to take the vector for each word in a post that people were making was also not that easy. And the reason being is that you know which words are there in the English language, but you do not know all the possible ways how people might misspell a word. So people are typically, well, not very good at spelling, especially on Facebook sometimes. So a lot of misspellings pop up. And also people utilize things such as emojis and so on. So basically what Facebook said is, well, every time that there is a word which is misspelled, we can basically just skip over it. Right? It's not in the vocabulary, so we just skip it, and we only take the vectors for the words that we do have in that vocabulary. But then we need to throw away a lot of information, because a lot of words are misspelled in our case. So what they decided to do is, well, let's just change, and this is kind of, you could call this the first step towards more modern tokenization schemes as utilized by large language models. And they said, well, what we can do is, instead of working with complete words, like a word like tomorrow, instead of putting each word separately in our vocabulary, we're going to tokenize it based on sequences of characters. 3 to 4 characters that occur together, and we'll construct our vocabulary based on that. And even then, if there is a misspelling somewhere in the word, then at least we have parts of the word that are still valid as well. And even still, that misspelling will probably also map to a vector that we do have. It's not going to be the exact one that we wanted, but most likely it's going to be relatively close nonetheless. So what FastText does, it's basically, it uses Word2Vec, but it changes the way how the tokenization is performed to work at the word sub-level instead of at the word level. And most LLMs nowadays also still do something like that. Now, you could also say, well, why not build a vector for each character, right? But then you only have about 26 letters and a couple of punctuation. Probably that's not going to be representative enough if then from there you would like to construct a representation for a full document instead. So landing somewhere in the middle is typically a good idea, hence why words sublevel tokens rather than character tokens. Speaking of documents, yeah, I already said something simple that you could do when you're in the situation where, let's say we have a small tweet or a post, and now I would like to have a representation for each of those posts, not just for the words, but for the post as a whole. Something simple that you could do is you just take the vectors for the words, you average them together. What you could also do is you could say, well, I'm just going to train my Word2Vec as I did it normally, but on my input side, I'm going to add in an additional token to the context. And my token, this first token, so I still have the one-hot encodings for my words themselves, just as I had previously, but now I extend my vocabulary, And I will say, well, not only does my vocabulary now consist of all of the words in the English language, like the and cat and sat and so on, but also based on the number of documents that I have, from document 1, document 2, or paragraphs, right, but documents just as well, I'm also going to create special identifiers, special words, if you will, that I'm going to add to the vocabulary as well. Things that do not show up in the English language, but special indicator tokens, like hashtag D1, hashtag D2, hashtag D3, and hashtag D4. And now when I'm training, rather than just giving the context consisting of the words that came before and after the focus word, I'm also, for every example, going to add in a piece of additional context, also one hot encoded, that's going to indicate from which document did this example come from. Right? So now the first 4 tokens in my vocabulary, these first 4 neurons, they will basically indicate does it come from document 1, document 2, document 3, or document 4. And then at the end, once I've done my training like before, what you will get in this weight matrix here, well, since now your vocabulary includes these 4 special indicator tokens, now you also have a representation for those indicator tokens as well, for the 4 documents as a whole. You can also throw away then all of the word vectors if you want to, and only keep those document representations. Drawback with this approach, obviously, yeah, now you can get vectors for each document, but again, the set of documents, because you have made those indicators part of your vocabulary, is again assumed to be known and of a fixed size. Typically, you would like to utilize things like these, not just for a set of documents that you have in a training corpus, but also on new documents that you want to utilize this on during inference. And so for that, this is not well suited. So we'll have to come up with different ways than if we would like to represent documents in a bit better manner. So averaging vectors might still be the better thing to do. Where these embeddings, like I already mentioned, also get applied in cases is you could also set something up like this to find representations, not for a vocabulary of words, but for levels in a high-dimensional categorical value. You could set up the exact same thing. Even if you're not planning to utilize a neural network at the end, and you still would like to use something like a decision tree or a logistic regression model, but you don't want to play with those dummy encodings because you have 500 different levels in a certain categorical variable, well, what this is basically telling you is why not first have a neural network that using only this one hot encoded representation of those 500 levels tries to predict, and very likely you will have a label in settings like these, tries to predict the label. Then you take the weight matrix of that neural network, you can throw all the rest away, and then that weight matrix tells you what the feature representation is for each of the levels in that categorical variable. And then you utilize those numbers to train your standard logistic regression model on. And again, rather than doing something like a weights of evidence encoding, where we basically mapped every level to a single scalar and in a bit more of a manual manner, also here you have the network learn what it thinks is the best representation to map those 500 categorical levels into a bunch of 4 numbers, for instance. So this can also work quite well. A simple neural network with only the categorical as input, an embedding layer, and then the label to predict, and then you just utilize those weights to represent your categorical levels. Again, same thing, if the day afterwards suddenly a new value for that categorical feature would show up, also this will not protect you from that, but neither do the other representation schemes. So this is an example where this is done, for instance, with days of the week. Not a very high-level categorical. The example is a bit contrived, but it does show, if you try to embed this into 2 dimensions, that it's not just a linear kind of line going from Monday to Sunday, but that some days of the week are more clustered together, and that Wednesday, for instance, is a little bit special. And in this case, this was an example about a retail shop, and basically what the model had figured out in this case, or well, there are days when the shop is closed, Saturday, for instance, and there are days when there is like a special promotion, and that was on a Wednesday. So that one was placed somewhere else in this embedding space. But same thing, if your categorical value would have a large amount of levels, you could set up something very similar. So to generalize, an embedding is just a layer where you map categorical items, inputs, a set of items to a vector of weights. And you have the network learn what the best weight values are for those vectors. trained using standard stochastic gradient descent, used upstream for some self-supervised task if you have to, or your label if you have it, and then with the goal to reutilize those learned vectors in different scenarios. And hence why we already said that dimensionality reduction techniques, autoencoders, that they also are techniques that create a representation, right? But there the downward goal in the case of PCA, for instance, it's to maintain variance. In the case of t-SNE and UMAP, as we saw, it is to maintain small distances between items. But also there, we construct a representation in a lower dimensional space with a certain goal in mind. Difference being that what also makes the setup of your architecture a bit different is that is your set of items expected to change over time? Is it something that you can learn once, like in the case of words, and then basically keep it around for new data? In the case of documents, a bit more difficult because there you expect that you also want to create representations for new instances in that vocabulary as well. And so for that, we'll need to try out or come up with different schemes than just doing something like this. This is another example. So these are words with positive and negative sentiments. So to give some ideas of visualizations that, or ideas that people have been trying them out for. A couple of years ago, some psychologists also did a word embedding association test because companies like Google, they have created sets of pre-trained representations for words in the English language. So these authors said, well, the fact now being that we can do analogy tasks, and you just gave the example of man is to women as king is to queen, let's maybe also try it out with a couple of other examples. Maybe we will try to say man is to computer programmer as woman is to, and the model will tell you, homemaker shows up there. So these authors found is that there is a lot of bias present in these word embeddings. But that's also to be expected, of course. These things were trained on, in the case of Google, of news articles of the past 100 years. Yeah, obviously there is bias in there, right? So there are ways to de-bias models like these, but it is certainly present, so also be a bit careful. Airbnb utilizes techniques like this to embed listings on their website, so to create a vector representation for listings on their website. And you might expect, well, you basically already have a good representation, the location of the listing, right? The X and the Y coordinates. Yeah, but if you want something which is richer and does not only take in the location, but also takes in the price and the square meters and the amenities and so on, then you maybe get a richer representation that you can then also reutilize in other models or maybe in your visualizations and so on. A master thesis student a couple of years ago also did something with word embeddings where she took all the news articles coming from Republican-oriented news outlets in the US, and then the same thing for Democratic-oriented news outlets in the US, and then also visualized the resulting embeddings to see if there were differences between these two sets of embeddings, these two representations. And indeed, here in this example, Trump is there in the middle, and if you go to spot where Obama is, you see that he's pretty close to words such as hater, loser, unfairy, deplorables, unpresidential, so you can guess which orientation that this representation is from. There is also, as we will see, once we go towards graph mining, and we will go to graphs as our data set, which will be our last stop in terms of types of data that we look at. Also there we will see that you can take Word2Vec, convert it into Node2Vec, and get a representation for each of the nodes in a graph. So here you get a vector representation for each of the nodes in your graph. And the idea there will be, we'll come back to it later on, but yeah, from Word2Vec, what do you need to have to make that work? A whole bunch of text to learn from. Now here you don't have text, you have a graph. Yeah, but there is a way how I can generate sentences from this graph. My words in my vocabulary, in this case, or my node identifier. So I have a word node 1, node 2, node 3, node 4, node 5, and so on. So just again, special indicator tokens. And to generate sentences, what I can do is I start somewhere in this graph at random, and I just walk around at random. And at every step, I have a chance to get tired and stop my sentence. And then I start somewhere else, and I walk around again. So I can generate sentences, which is basically, in this case, sequence of token visits with their identifiers, by just randomly walking over this graph. And then I can take that whole quote-unquote text that I have, dump it into Word2Vec, and I get a representation for all of the nodes in this graph. Works surprisingly well. It's it's even fun to tweak the way how you're randomly walking around in your graph and then seeing how the resulting representations differ. Now, what do we then do with these representations? Yeah, you can visualize them in a certain way, but then you can run k-means, for instance, on top of them, and you have something where you can do some sort of clustering or community detection on top of a graph in a relatively straightforward and also efficient manner. So that's another example. Okay, this brings us then as our next stop to recurrent neural networks, but I see that it's time for a break, so let us first go for a 10-minute break. Okay. So, recurrent neural networks, what's the idea here? So, with text, you already mentioned that one of the embedding models that we just saw, Word2Vec, works reasonably well, but we don't have yet a, let's say, very elegant solution to get representations for documents as a whole. So that's something that we would still like to fix in a way which is a little bit better. And related to that is also the fact, well, not just for documents of text, but also if you look at data sets such as time series-based data, where every instance could be a series of measurements, for instance, is that we can wonder in general, okay, how can we set up an architecture where we can learn from sequential data, where we have something where the instances can have a varying length, like is the case of our documents, where we would also be able to take the order into account a bit better, and then also with the, let's say, downstream task to maybe complete the sentence in the case of a language model, or maybe predict something based on the given input sequence as well. So how do we deal with sequential data? That's the question that that's the question that the recurrent architecture will help us with. Of course, what we could do if you look at something like time series or text, we could still utilize a window-based approach. We have already mentioned last time or a couple of weeks ago that you can utilize one-dimensional convolutional neural networks on text as well, right? So basically you can set up something like that, or in the case of time series, you can construct lagged features instead and try to tackle it that way. Or you could first use something like a Word2Vec model and try to break down the full sequence or collapse the sequence down to a single vector and then work from there. But now we're looking for something that in the architecture itself can help us to learn from sequential data. And that's what the recurrent architecture will help us to do. So note that we could not get away by just using a standard multi-layer perceptron in this case, because if you think about our input layer, there we do need to decide how many neurons that we're going to provide. And if we just say, well, but now we have things that are of a varying size because we have sequences, and these sequences can be of different lengths. Maybe theoretically, we could even say that maybe an input sequence can go on for as long as it wants, and maybe after every step you need to predict something, but the input continues to arrive endlessly, for instance. How do you set up an architecture that can deal with that? And the idea of the recurrent architecture, it's not so difficult. The idea is that we're going to set up a new type of neuron where the model will only see the current input, so we'll go over steps in the sequence. So when we say current input, we mean the current step. So we'll feed the inputs, the steps in our sequence, step by step. So the inputs are fed to the model sequentially. So in the case of a piece of text, again, there, I could say that my text is a sequence of tokens, and I can represent every token in a one-hot encoded format, and then basically I'm going to feed each token, each word, step by step to this model that I'm going to build up. And maybe up until I'm done by giving it the input sequence, and then the model can utilize that to make some sort of prediction or generation or completion based on that. That's the idea. Now, since I'm feeding these inputs step by step, it seems reasonable that this model or this architecture will have to construct some sort of, call it what you want, some sort of state, if you will, some sort of memory that it needs to retain as I'm giving it the different steps in this sequence, the different inputs in this sequence. Or in other words, what I'm basically looking for is that as I'm giving the
inputs in this sequence step by step, that this model stepwise builds up some sort of internal compact state again. So again, it's about compression, it's about representation. I need something where I can feed each token of my text one by one, but over those steps, the model then constructs a representation of, at the end, the text as a whole. And then I have something where, again, at the end, I can extract a representation that I can then do something with. So it's an alternative for the Word2Vec-based scheme as we just saw, and theoretically something then that should be workable with any new piece of text that I give it to. So now this is not fixed and limited to a specific set. This basically will help me to then enable me to give this a new piece of text, and it also builds up a state representation. So it also constructs a representation for me. So that's what the recurrent architecture will do. They are called recurrent because they perform the same task for every element of a sequence. You could think of it as being a for loop, but expressed as a neural unit that we're going to build. And the for loop will be, well, for every item or input in this sequence, construct something, do something. The output then will be dependent on the previous computations. Okay, let's take a look what that means. So the basic idea will be that I want to build something that looks a little bit like this, where I give it the features or the inputs at a particular step, the step that I'm currently at, step T. But if I would just look at the left-hand side, this would just be the same thing as a standard densely connected network. But the idea is that the network is going, or this unit is going to utilize this to then construct or to output some state values. You could think of this as its internal memory, if you will, just a bunch of numbers again, a representational vector, where the update in every step of those state values does obviously not just depend on what I'm giving you at the current step, but also has to depend on what your previous state output looked like. This figure is maybe a little bit complicated, but we'll see an example where that becomes clearer. Basically, what we will do, and this is maybe a bit easier to visualize, is something like on the left-hand side. What I want is, and I will use the example of text, let's say, and let's say that I start with, I like cats very much, and let's say I have whole pieces of text like this, and maybe my task that I'm trying this, or that I want to set up, is maybe I have a label, and I need to predict whether this is a positive piece of text or a negative piece of text. So a simple sentiment prediction model, positive or negative, binary classification, something like that. Problem is that for my documents, that these have different lengths. So I could try to figure out a way to squeeze them down to a single vector. Maybe I can use Word2Vec, average the vectors, and I could use that in my traditional MLP setup. But I don't want to do that. I would like to retain both the sequential nature and the varying length nature of the data that I have. Maybe the second sentence is, I hate cats, something like that. So what I will do, again, I do need to, even if I will work step by step, let me see if I have some other color. And I will deliver these words in a step-by-step manner. I still need to deliver them in a way where it makes numerical sense to my network. So what I'm probably going to need to do, as always, is I will construct some sort of vocabulary of tokens. And to make my life simple, I'm just going to use words again. But remember, in the case of language models, I could also use parts of words. I could even use individual characters if I wanted to. So basically, I will deliver my inputs like this. And my vocabulary consists of the words like I, like, hate, cats, very, and much. And so for my neuron that I have here, this RNN unit, the idea will be that I feed the input step by step. So the first input that I need to feed is the word I. And I'm going to give this, like always, I don't have much choice, just as a one-hot encoded bunch of inputs, so a vector with, basically, let me just draw it like this. Well, no, it's actually an input layer, so let me add that in first. We have the number of units equal to my vocabulary, one of them outputting 1, the others one being 0. So those are the inputs that I'm going to feed in this RNN unit. First, for the word I. At every step, this thing will do the same thing, right? It will, using some mechanism that we don't know yet internally, it's going to output me its updated state vector. And that state vector, well, the state could be a single number, and then I can create a vector of those things simply by putting multiple RNN units in the same layer, basically. So I can have a layer of RNN units, and each of those guys updates me with a new number. So I get a state representation. So after the first word, maybe the vector that I get out of here is 0.8, 0.6, 0.0, and 0.1. Basically meaningless, but it's building up some sort of representation. So this is what it says. This is my current state, my current representation of the sequence thus far. I'm not done yet. I then move on to the next word, like. My one hot encoded will change here because this will become 1, because my word has changed. And again, this will update its internal state. But to do that, it needs to, of course, also get as an input, hey, what was my previous state? So at every step, I give it the current input represented in one hot, for instance, of my document, but I also give it its previously produced state as well. So an RNN unit needs two things, the input at the current time step and its previously generated state. Wait a second, for the first word, I, there was no previous state there, right? So then what do you give there? Well, again, you just randomly initialize those states somehow, right? Make them all 0 to start with, for instance. You need to start from something. So that's your first initial state. Once you're done, at the very end, so once you have given it the last word, much, again, this thing will update its state, and if there would be a word afterwards, I would again feed that back in together with the new word, but now there is no word afterwards. What can I do then? I can say, well, now this state representation, this vector, is what I hope to be a good representation of the full sequence now that you fully parsed through it. And then I can take this vector, which does have a fixed length, add a dense layer of neurons on top of that, and then another one, which makes me a final prediction between 0 and 1. And then I can train this thing. Now, the backpropagation will be a little bit nastier, obviously, to set it up, because what looks on the left-hand side as some kind of loop, of course, becomes unrolled over the different steps that you have in each instance. So hence why here we need to perform backpropagation through time. We need to unroll from the right of the sequence all the way back to the left-hand side. So typically, this is a bit more nasty to train, but again, luckily, we have automated differentiation engines that help us with that. Setting this up manually or deriving this manually is not so fun, but luckily, the libraries help us with that. So it's same as regular backpropagation, but the graph is, the computational graph is unfolded over time. And weight sharing is applied between the time slots, obviously. So the internal weights that it will utilize, if I would open up what this unit does, and it takes both the current input and its previous state, and it produces an updated version of this state, probably also by multiplying with some weights. Once these weights are trained, well, they're there, and we reapply them on new sequences on every step of that sequence, right? So there is weight sharing between the time slots as well. Crucially to note, though, is that this is not the same setup as a setup where you would simply utilize an MLP and give that the current input and the previous input. That's not what happens here. We give it the current input at the current time step, plus its previously produced state. And to know that previously produced state, you need to start from the beginning of the sequence and work your way towards the end of the sequence. Now, also what you will see is that the state update happens both in training and in inference after every step. So already after I've given it the first word I already get a state vector. If I then give it like, I get a new state vector. Now, typically, it depends on the task, right? I could do something with those intermediate states as well. But in most cases, what I will do is I will basically wait until I've gone through the full sequence, or the full sentence in this case. I will take the final state vector, and I will give that to a dense layer to then perform a final prediction with, to tell me whether this is positive or negative. But theoretically, you could already, intermediate, also do something with those representations. Maybe you could trade it in such a way that you want to predict to complete a sentence, and then already after every step, you can use a state vector to let it predict what the next word in the sequence should be, right? And then in the next step, you have it predict what the next word in the sequence should be. So that's also something to note. And also important is that theoretically, since this thing keeps going, the length of the sequence that you have it go through can theoretically be as long as you want to, right? But you can already kind of feel that if I would give a full book to this thing, that by the time it's at the end, that this state vector, I can make this 1,000 numbers long, but that probably it's going to be hard to represent a full book in a single state vector of 1,000 numbers. It's probably going to focus more on the later parts and probably already would have forgotten a lot about the beginning of the sequence, right? So it's not all powerful. You can't squeeze the complete Lord of the Rings trilogy in a numerical vector of 1,000, but maybe for shorter texts or for simple classification and so on, this would work. And like I mentioned, RNN training is hard because, yeah, our problem of vanishing gradients, because we're now doing backpropagation through time, comes back. How we set up this initial state, we also need to be a little bit more careful here. This is a non-linear dynamical system, so small weight changes can make the system unstable. So it took a bit time before, let's say, libraries and packages and approaches were clever enough and good enough to train such RNN units in practice. But nowadays, it works quite well. So the thing that we need to then wonder is, okay, I do know that at every step I give it the current input, and this H thing is its previously produced state. That's what we call the hidden state, if you will, hence the H, its representation so far. So in this case, both this arrow and this arrow, they're the same, right? So basically, I give you the current input plus your previous produced hidden state. And at every time step, you also update your state. And typically, I wait up until the end to then do something with that final state and maybe predict a classification task or something like that. But I could also use the intermediate states as well. So I have something where I want to give this an input, maybe a single number, right, or a bunch of numbers. And it needs to produce me with a state. And I also need to feed that previous state in itself as well. What does the inside then look like? Well, for instance, I could say something very simple, like a 10H. For instance, I could say, well, combine your previous state and the current input in some way, apply a symbol activation layer on top of that, a hyperbolic tangent, and the result of that is how you update your state. So basically, you mix, using some weights, you combine the current input and your previous state together to update what the next value of your internal state should be. Okay, maybe a bit more reasonable, or an example that makes this already, let's say, a bit more concrete, is the following. So we could say, well, at every time step, I give you the current input x. I also give you your previous, hence t minus 1 produced state, and the first one starts with all 0, let's say, or something random. I have two sets of weights, so now there is something that can actually be learned in this thing, right? So I'm going to perform a weight multiplication, so I have a set of weights here, and I have a different set of weights here. So I have a bunch of weights that gets multiplied with x, and I have a bunch of weights that get multiplied with this a thing. The weights are independent of the time step that I'm currently at. So it's the same weights that get applied no matter what this value of t is, whether I'm at the beginning of the sequence or at the end of the sequence. So the update mechanism is the same. Doesn't mean that the unit here has no way to kind of know where it is in a sequence, because the whole idea is that the way how it will construct its state, if it is important to keep track of the fact that you already have seen a whole bunch of inputs, it will probably put that somewhere in its state. It could be just something as simple as maybe one of the dimensions in this state just gets added with 1 at every time step, and then you have a way to keep track of how many items you have already seen. But it's the same weight multiplication that happens. We add those together, so that's what this plus is. Yeah, a bias, like always, and then we squeeze that through a 10H to get something between -1 and 1. And that's then the update of this state. And then what you can also do, if you would like to do some prediction tasks, you can say, well, the last one, you put a softmax on top of that to make maybe some prediction based on that. So what you put on top of that hidden state, that's up to the task. That's up to you what you would like to do with it. Do you want to do regression or completion or classification or something like that? So Relatively simple in the sense that, well, basically how the new state gets produced, it can be clever enough to kind of multiply or use the previous hidden state that it produced as well as the current input, and then mix them together, combine them together to create the new state values. But it's still relatively simplistic in the sense that if I would now give this thing a very long input sequence to work over, that very likely, like I said, it's going to be pretty tricky to retain or to capture or to represent that full input sequence in that state. And moreover, if this kind of approach, if I have something that arrives pretty early in my sequence and turns out to be pretty important to retain, that it's also going to be quite hard, if you think a little bit about what this thing is doing, to retain that for multiple time steps, to keep that information in that state representation for multiple time steps, right? Because basically your weights would have to work in such a way where if there is something present in your previous state representation that indicates that it's important that you do retain that, but then it gets added with this thing. So how do you avoid that over time, those values in your state representation that do not get washed out or mixed out by new inputs that arrive? That's perhaps a little bit tricky to do correctly here. Theoretically, it can learn that, but you would need a lot of data and a lot of training in order to make that work. So tend to forget information in longer sequences. So there is another unit that was proposed, called already in '97, called the LSTM, the long short-term memory unit, and that tries to make it a bit more explicit in terms of how it can work with that state representation. And especially for cases such as, well, let's say that I'm working through a piece of text, or maybe I'm generating text, and maybe already a parenthesis or a bracket has been opened already. Yeah, I do need to retain them in my state representation, that this is still something that I need to close later on, and I need to keep that with me for multiple time steps. So that's something, but then once I have closed the parentheses, I basically immediately want to forget that piece of information. I immediately want to zero that out. I do not need to take that into account any longer. Once the parenthesis is closed, I do not need to keep track anymore of the fact that there is some signal here indicating that there is an open parenthesis at all. And this unit does so by introducing a mechanism called gating. And gating means that it can also learn to conditionally set or reset, and typically in the case of a neural network and a vector, when we say reset, we mean setting it back to 0, one of the values, based on the current input and the previous state. So it can be more aggressive in terms of values that it wants to zero out in its state representation. Also note that it works with the current input. At every time step, this thing produces two states, something called the cell state and something called the hidden state, for whatever reason. So it builds up two state representational vectors, and it passes both on to the next step at every time. Interesting, or what is noteworthy in here, is these little sigma in here. So these are sigmoids. So basically this helps it to basically learn, if my current input looks like this, and my previous states, they look like that, then I should be capable to multiply parts of my state vector with values between 0 and 1. And if I want to multiply my state representation or a part of it with a value that is close to 0, I'm basically saying, well, now I can forget this part of my representation. So it can be more, or it can more explicitly learn which parts to retain and which parts to forget at every position of your sequence. This is an alternative called gated recurrent unit, which is somewhere in the middle in terms of complexity. They train a bit faster than LSTMs because they are not so complex. In theory, LSTMs should be better capable to work with longer sequences, but very often the gated recurrent unit is also chosen as the default unit type. Then, so what to do with these things? Well, like I already mentioned, text completion. Now you can basically say, well, I give you a piece of text and your task is to learn to complete the text as well. That might seem a little bit tricky if you think about the setup, but we'll immediately see how we do that. What I can do, let's say that I have a sentence, such as I like cats very much. I just said, well, since I have a state after every time step, I can basically use that state and have it predict the next word in the sequence. And then I can use this as the input sequence and have it predict the next word in the sequence. that is a little bit different still than, let's say I give this thing the text as a whole, right? I like cats very much, and now I want you to complete or to predict not just the next word that will appear, but a whole bunch of words, right? How can I set this up, right? And you might think about different ways. You could say, well, maybe it's sufficient that you just predict the next word and then you can feed that back in and you auto-regressively try to complete your sequence like that. But maybe there are other ways that we can do as well. So how can we go from sequence to sequence style modeling, where the input is a sequence, but I also want the output to be a full sequence of text or whatever as well. We'll immediately see how that approach works. What we can then also start playing with is we could start making combinations of the convolutional neural network units that we saw previously and this RNN style of approach, right? Nothing is stopping us from saying, well, maybe I have a video and a video consists of a sequence of image frames, but instead of directly dumping that raw data in this RNN layer directly, I'm first having a stack of CNN layers, for instance, that can convert the image to a better representation for that image, and then I basically have a sequence of that, and the RNN can maybe learn to do image segmentation and things like that on video rather than just a static image, or maybe even things such as video completion and generative tasks like that. What is also, or was sometimes also done, is still sometimes done as a trick is, since these things can have trouble with longer sequences, and if my task is of such a nature that I first would like to crunch through the full sequence, then use the hidden state representation that I get at the end to give to an MLP to tell me, okay, what's the sentiment of this review? Is it positive or negative? What I could also do, if I know that it has a tendency to forget stuff from the beginning of this sequence, I could also feed in the sequence from right to left as well then, and use that hidden state representation as well, right? So basically go through the sequence from left to right and also from right to left. And that's called a bidirectional RNN approach. In this case, however, note that this is not the same as cheating and looking at the future, right? Even if your task would be generative, for instance, and you would like to complete text or generate text, the input text so far, I can also just deliver from left to right and right to left, right? I know the input so far, at least. So the order in which I deliver that doesn't mean that I'm cheating, right? I still can do with that as I want. You still need to generate or complete the text that comes afterwards. A bit strange that we have to use tricks like these, but sometimes this helps a bit when working with RNNs. This is then the sequence-to-sequence model. And the idea here is, okay, now can we set something up where maybe we're trying to do something like text generation, for instance, or maybe let's say that we want to set up a mechanism, which is where these models were initially used for. I would like to set up a translation model. And the idea is, when I'm translating from source language, English in this case, I like cats, and I want to translate that into French, that basically for my input sequence, I will first deliver you the full input. Those hidden states that you construct here as intermediates, I don't really need them. I basically would like to take that final hidden state as my representation for the full source language input sequence. And then I would like to take that hidden state, and from there I would like to make a translation to generate the output text, but now there I have the same issue on the output side, namely that I do not know beforehand how many tokens does this thing have to generate on the output side, right? If I have this thing always predict the next word, then it's the next word, but I want to also utilize a recurrent mechanism on the output side as well, and that is what a sequence-to-sequence model sets up. So the idea works as follows. It looks a little bit like an autoencoder style setup in the sense that also here we have an encoder and we have a decoder. And on the encoder side there, nothing very special or weird happens. Basically, I feed my input sequence, I like cats input by input. Remember that at every step it uses the previous state vectors as well as the current input, and since I'm using an LSTM here, I have two state vectors, H and C instead of one, but you can just think of it as one state vector if you would prefer that. But at the end, once it has seen the full input sequence, I have my state representation. So basically this encoder is learning how can I squeeze this English sentence that you've given me into a vector representation that then the decoder can translate off from. So once the encoder is finished, it produces a representation, a vector, for the full sequence. Then it's the decoder's turn. And also the decoder, well, it's an RNN unit. It might appear that here there is 3 of them, but it's just one unit that we repeat over multiple time steps. And for the initial hidden state of the decoder RNN unit, I give it the produced representation by the encoder. So here I do not start with a random initialization for the hidden state. I give it the representation that was produced by the encoder. I then want this thing to generate me the translation. But since this is recurrent as well, I need to give this also a sequence to translate off from. But in the beginning, I haven't generated anything yet. So as my first token that I will give this thing, I'm going to use a special token that I've injected in my vocabulary to indicate that this is the start of sequence. I'm basically telling this decoder, there is nothing so far. You do have your hidden state that the encoder has produced. We are at the beginning of the translation. What should the next word that I add to this sequence be? The LSTM will update its hidden state, and I can use that with some dense layers on top of that to then say, okay, predict me what the next word, or tell me what the next word is that you want to generate. So again, there at the end, that will probably be something one-hot encoded, right, that I can sample from or take the most probable word from. And likewise for a language model that needs to complete text rather than translate text, then this would be your user question, and this would be the reply of the model, basically. Same thing. In this case, out of that softmax layer, I see, well, the next word that it wants to generate is j'aime. Okay. Maybe better if it would have split up je and aime separately as tokens, but whatever, it's an example, so j'aime. It also updates its hidden state. So in the next time step, what will I give it? Well, its previously produced state that has now been updated, as well as the word that it has just generated. So I feed back in its last generated output as the current input as well. And then it tells me, now the next word that I want to generate, that I want to add is le. And then I give that. And this continues, so this is auto-regressive generation, and this continues until my model will produce me, again, a special token indicating end of sequence. I want to stop. I have no other word left that I would like to add. So also end of sequence is a special token in my vocabulary so that this decoder has the opportunity to say, I stop here, I'm done. And this is basically then how you can, in translation tasks or in language tasks, how you can set up the generative models or translation models. Now, if you would like to set this up, this will work, but there is a little bit of an issue with this setup. And the issue is that first the encoder gets to work and takes in a full input sequence, and the encoder's job is, please try to squeeze this blue part, the original sequence, in a context vector as good as you can, that we will then pass to the decoder, and the decoder will then start generating the translated version, or the output tokens, in the mechanism that we saw in there. This is not easy. For short sentences, this might work, but again, here, if your input sentence gets longer, to squeeze that completely down into a single representational vector to then translate from, not an easy task, obviously. Right? Now, if you have a whole text to translate, you could do it sentence by sentence, but then maybe this thing might miss links between sentences and so on. So is there a way that we can make this a little bit better? And what you will note is actually that, at least in this case, but also if we would ask a language model, and this should be a question, and the model is generating its reply, that depending on where you are in your generative process, in this case in your translation generation, right, depending where you are in your output generation, that you might wish to look at different parts of your input. It doesn't make a lot of sense that we first ask this encoder to squeeze everything down to a single vector, that this then has to do everything with. It would perhaps be better that during the decoding, it can refer back to the full input sequence as well. And now you will hear something coming, of course. It would be nice if the decoder could attend to different parts of the input sequence depending on how far along it is in its generation. And there we come to sequence models with attention. So attention, a mechanism that we can attend to the different parts of this input rather than first squeezing it to a single context vector. For translation, this is very logical. There is, okay, languages differ a little bit, but of course, if you're busy in the beginning and you're generating ta, of course, you're looking at she, right? If you're later and you're trying to generate pingwo, well, then you're later also in your input sequence, you're looking at apple. So how do we do that? Well, now, this is basically saying what I already mentioned. So unreasonable that we can encode all the information of a very long sequence in a single state vector. So we're going to introduce attention. And attention reduces the dependency on a single vector encoding by learning what to focus on in the input sequence during the output generation process itself. Okay, how? Well, there are two key differences with the setup that we have just introduced, with the standard sequence-to-sequence model. First is, instead of only passing the last hidden state of the encoder, we're going to utilize all the hidden states of the encoder. Why only work with this last state? You're generating intermediate states as well. I'm also going to use them, right? Why not? I have them, better utilize them. So that's one change that I will make. And another change is an extra step before producing the output. The decoder will attend to different parts of the input sequence by calculating attention scores and softmaxing them and then multiplying them with the input. Okay, let's take a look at what that basically means. So this is we are at our translation task again, and we are already in the output generation process, and we are at time step 4. My encoder, there nothing much changes. My encoder still goes through the full input sequence, I like cats, and is giving me hidden states for each step. So those are the orange vectors that you see here. The C is not shown, only the H. Those are the encoder hidden states. I have one after I have one after like, and I have one after cats. The size of each of these columns that you see, these 4 blocks, are set beforehand, right? So they stay the same. The number of columns that I have will obviously depend on the length of my input sequence. Here it's 3 because I have I like cats, but if my sentence would be longer, I would have had more of these orange columns. So that's annoying. I still have something here of variable length that I will have to deal with somehow, but we'll immediately see how. The decoder, so the thing that's currently busy generating the translation in this figure, at every step in the decoding process, the decoder also has its own internal state, right? So also the decoder has its hidden state at the current time step. The idea is now that somehow we're going to calculate, given, okay, this is my current state, and this doesn't change at every time step. So these orange blocks, their values also stay the same at time step 3, 4, 5, 6 of the decoding process, right? The encoder is finished, the orange columns are there. I'm going to calculate attention scores, and basically they are going to represent, well, given where you are currently at, given what your internal state currently looks like, and given your current input as a decoder, and remember, the input for the decoder is the token that it has just generated, right? Given that information, what do you think should be more important to look at in these 3 columns that you got from the encoder? So you calculate attention scores, but yeah, we want something between 0 and 1, so we softmax those scores, and then we multiply those scores with those 3 columns that you see there. So if the score here is high, means, well, this we want to keep around, this is important at this time step. These 2, they are not important. We don't need to attend to those so much. So multiplication here basically means that these values become very low, right? Close to 0, it's like they're not there, right? We're attending them away or we're hiding them. Now, since here we have 3 columns because I like cats, but if I have a longer input sequence, I have more columns. That's not nice to work with. I need to reduce that to something that has a fixed length for the matrix multiplications to work. But okay, since most of these things now are 0 anyway, except for the things that matter, just sum over the columns. And then you get a single vector for this time step that you can then utilize to generate what the next word in your translation process should be by slapping an MLP on top of this thing. Something like that, right? The next time step, This vector now is context dependent because this changes as you are attending at different parts of these orange values over there, right? So the blue vector changes, also the purple one changes because we'll still update our internal state. So we get something that looks like this, right? So here my encoder has produced all the hidden states at every step, and then at every decoding step, I give you your previously produced output. In the beginning, that's a start of sequence token, remember, or an end token in this case, doesn't really a special token, right? In this case, I do not take this last column anymore as the initial state of the decoder, like I did previously. I just start with a random initial state again, right? But at every time step, I calculate attention scores, I multiply, I sum to get this blue thing, and I combine this blue thing and your updated state to then put an MLP on top of that and to predict what the next word that I want to generate should be, I. Then I take this word, I feed that in as the next input, and again I do the same process over again. I calculate new attention scores, I multiply, I sum, I have a new blue thing here, I combine this with your internal state, and I push that through the MLP again to predict the next word, M. And also this continues until the decoder says, I predict end of sequence, I want to stop. So now you have something that in the decoding process can look at different parts of the input sequence. Okay. We do not know yet exactly how these attention scores are calculated, but that will actually be the easy part. But there are some questions that we can make here or that we can observe. First of all, I'm attending to the input sequence. As I'm producing my generative outputs, I can pay attention to maybe the first word or the second word and so on. But here I'm attending to things that themselves are already, every column here is already a representation produced by this recurrent encoder over the input sequence. But do we need to make that so troublesome? Why bother having an RNN encoder at all? You have your input sequence, it has a variable length. Why not just use something like an embedding layer, where we just convert every token into a vector without having to have this whole recurrent process? Is it important that the encoder here is recurrent? Probably not, eh? Whatever representation that we can get for the input sequence is probably already sufficient. Maybe even a one hot encoded representation could be okay, who knows? Typically we will use an embedding layer there, but maybe we do not need a recurrent encoder anymore. And then also for the decoding part, maybe it's a little bit more tricky to see, but you could also wonder, do we need to make this recurrent as well? Is there a value there that we have a state that gets updated and the previous output gets passed in? Do we need this state update mechanism, basically? Couldn't we get away by just using attention scores alone, together with your output that you have generated so far, and no updating state mechanism? So no recurrence on the output side as well. And indeed, it will turn out that that is not only doable, but also advisable. And in that case, and hence the name of the famous paper, Attention is All You Need, came after this and basically found that, wait a second, with the attention mechanism, that's already sufficient to generate text and to do translation and to build LLMs and so on. You actually don't need recurrence at all anymore if you have attention. And hence why we entered the era of the large language models. Now, if you look at these attention scores, or so these are the scores at every time step at the translation process. So I have here 3 hidden states. It's not I like cats, je suis étudiant. I'm producing with my decoder my translated version. If I visualize at every time step, so every column here, the attention scores that are being calculated, you can see that they correspond pretty well with the input sequence. If I'm at the beginning, I'm paying attention to je. If I'm at the end, I'm paying more attention to étudiant at the end. So indeed, here you can see that as I progress through my decoding, that I get different attention scores that map pretty well with the positions of the input sequence. And you can, even for longer sequences like this, the agreement on the European Economic Area was signed in August 1992 and an end token. You might say, yeah, but it's easy, there's always a diagonal line. Not always, because in French, some words get swapped around compared to the English, and you can see that the attention scores change similarly there. The way how we calculate attention scores, there are different mechanisms that have been proposed throughout the years, but the scaled dot product is the most commonly used one. It's still used in every LLM as well. So it's basically a normalized version of the standard dot product. And basically what we would like to calculate with these attention scores is, what we will do here is, the way how we calculate these scores is we will talk of a query, a key, and a value. And that's how we'll calculate these attention scores for. The query is a thing that I'm basically using as a lookup. And very likely my query is the decoder hidden state at my current time step. This is my Q vector. My keys are, okay, what are the vectors that you want to look in to retrieve which are the most similar one? It's almost like a dictionary in Python, right? Your keys are your unique value, and your query is the key that you want to retain. And with a dictionary in Python, either it's in the dictionary as a key or it's not in the dictionary as a key. So there you would get values that are zeros and ones, right? It's either in there or it's not in there. If you have keys A, B, C, D, and your query is A, well, your vector of values that you would get back is 1, 0, 0, 0. Right? If you would ask for a query of E, well, it would be all zeros because it's not in your dictionary. Here you want to do something similar, but not so harshly, a bit more softer. And we would say, okay, or my keys in this case, or vectors, my query is also a vector, and basically I would like to see how well my query vector matches with my key vectors. And depending on the size of the match, I would like to I will return, or I will assign these attention scores based on that. So the query in this setup, at least, is my, what do I want to look up? My current vector representation, in this case, this purple thing, the decoder hidden state at this time step. The keys, or what do you want to compare with? Well, that's this orange bunch, right? My keys here are the hidden states that were produced by the encoder. The values are, well, if you do find a match, like in your dictionary with Python, what would you like to get back? What's the value that you would like to get back? So what will you multiply these softmax attention scores with? Also the orange thing. So in this case, the values are the same as the keys, right? So you multiply after softmaxing, you sum up, and that is how you get your softmaxed attention score. Just your query transposed times the k divided by a normalization factor. With this setup, we do no longer need our encoder to try to squeeze the full source sentence into a single fixed vector representation. The network can attend to different parts at each step of the output generation. The transformer model is based on this and also does away with recurrence. And it will also make use of what we will call self-attention. And self-attention meaning that both the query, the key, or the keys and the values come from the same set. In this case, that's not still the case here. Our key and values are the same, but our query still came from our recurrent decoder that was updating its state mechanism at every time step. So if we do away with that, we don't have that purple thing then anymore. We don't have an RNN on the decoder side. So we need to utilize something else as our query in that case. But maybe we can do that, right? And indeed, that's exactly what the transformer architecture found. So, so far we are kind of like before the advent of transformers. So for a long time, Word2Vec, GloV, and so on was pretty popular. FastText is also relatively popular, but nowadays, of course, since 2017, since the GPTs arrived, we have basically all but completely switched to this transformer architecture for text tasks, and in some cases also for vision tasks, as already mentioned, by representing patches of images in your token vocabulary as well. This timeline is already horribly out of date, but it tries to make some attempt to kind of show how this attention mechanism then grew up to become, from WordTech, FastText, and GloV here at the bottom, techniques such as BERT, Roberta, BART, and so on, to the GPT angle, and which has basically grown up until, well, all the LLMs that we utilize nowadays. Interesting here, which we will not go into too much detail of, but interesting is we will throw away the recurrent mechanism. We will heavily rely on attention instead. But something that you could still wonder about is, well, do you still set this up in an encoder-decoder style way, where you first have some encoding mechanism that is then perhaps not recurrent in nature, but where you still try to parse your input sequence first and prepare it in some sort of representation? Or is there a way where you can maybe do it with the decoder part only, and you do not need a special encoder anymore? Or in maybe more extreme cases, maybe there is a way to do it with an encoder only in some settings, like techniques like BERT. Since the majority of large language models nowadays and techniques are decoder only, that is also we'll focus on and kind of show how the mechanism of attention works if you only use a decoder and you do not use recurrence at all. So this is the Attention is All You Need paper. There they still worked with a stack of encoders and decoders. The encoders later then were thrown out. It was found that that's not necessary. And our query key and value come from the same set, so we will make use of self-attention. And basically all the techniques that you can find in this huge family tree, they all make use of self-attention as well. I will utilize these examples a bit later on to kind of end with a visualization, but let's first take a look. So here, this figure typically shows also both the encoder part and the decoder part. Instead, what we will do is only use the decoder part. So what will the idea be? So the idea is that we now have an input sequence, and if it helps you to think a bit about it, we can think of our input sequence now not as it could be, something that we want to translate, but of course, typically in the case of a large language model, your input sequence is the prompt of the user, the question that has been asked, right, that you need to then provide an answer for. What we will do is probably we'll have an embedding layer, so we'll cut up that input sequence into tokens as we did previously, probably not words, probably pieces of words instead in the majority of cases. And we're going to have an embedding layer where every token in our vocabulary then gets converted to a vector representation. So that we still keep. So here, every token in my input sequence is maybe a vector of 3 numbers long. Very little, typically it's more, but it's to fit it on the example. What I will also use, because I will not use a recurrent mechanism and I want this thing to be able to work on the full input sequence as a whole, I will use some concept of ordering by doing it this way. And that's a pity. That's something that I did get with my recurrent mechanism. That's something that I lose again here. So basically, I could order these input tokens around. I would have a new sequence, but to the network as a whole, it wouldn't make a difference. And the difference is, of course, due to the way, as you will see when we are decoding off, as you already saw in the previous picture, they were basically adding the multiplied value vectors that we have here together, then the order of that doesn't matter, right? If I swap those around, nothing is going to change there. Now, how do I keep some ordering intact by doing this procedure in there? Well, most transformer models, not to say all of them, and also every large language model also adds in a positional embedding as well. And a positional embedding is, again, a representation, and a simple positional embedding would just be the numbers 1, 2, 3, 4, 5, and so on. But basically, it's also a vector with the same length that we use for our different tokens, and tries to come up. I do think I have a picture maybe somewhere, or maybe not. Yeah, here. And tries to come up with something that is a bit more stable and robust. So this is a vector as the position increases. So here I can have an input sequence of, what is it, 500 words, and these are the values of that positional vector. So that is basically a vector that indicates, not only is it this word, but this is also an indication of where that word is in the input sequence. And then the idea is, if I go back to my original figure, that we mix in that positional embedding with each of the tokens that we have. So here I also have 4 positional embeddings, 1, 2, 3, 4, and I mix that in to kind of tell, well, not only is this the word cat, but also it's at the first position. And not only is this the word like, but it's at the second position, and so on. So then I do still retain some information indicating the position of the input sequence that I can give. So that's the first part. Then the idea is that I have a stack of only decoder blocks. And my decoder blocks will produce output token vectors that can then get transformed into tokens to generate, words to generate. This decoder block obviously does most of the heavy lifting, uses a form of normalization called layer norm, a bit similar to batch normalization, but works on the complete layer to keep activation values a bit under control. A fully connected neural network, so just an MLP, and the key important thing is something called masked self-attention. So we embed a sequence of tokens, add positional embedding on top of them to mix in positional information, apply self-attention, and then some layers on the top to softmax out the next token that we want to generate. When we're doing inference, we will, same as what we did before, we will also auto-regressively take the output that my network has said, well, this should be the next token. We add it into the input sequence, and we from there predict the next token. So same thing here, every time, or LLM here in this case, predicts the next token, I take that, I stitch that into the input sequence, and I ask it again what the next token should be. I also take that token, I put it into the sequence as well, and I ask it what the next token should be. So basically during inference, this is kind of an autoregressive loop construct, where I start with the prompt of the user, you give me your first token, I feed that back in, you give me your next token, I feed that back in, and I autoregressively complete the sequence like that. A decoder block mainly consists of self-attention, a dense layer, and some residual connections, some skip connection, but obviously it's a self-attention mechanism here that does the majority of the work. For each token, so here we use that self-attention mechanism, what can this layer do? Well, no recurrency anymore, so that's not what we can do, but we see the full input sequence so far. So we're going to calculate attention scores. So we have a query, we have a key, and we have value, and we will have 3 different weight matrices, and all of these 3 are derived based on the same set of tokens. Which set? Well, the input sequence. They all come from the input sequence. So I will, again, compare with my input sequence to calculate, okay, which parts of the input sequence should I give a higher attention score? I softmax these attention scores, I multiply with the input sequence, and I basically create new representations of my words. So by multiplying with these attention scores, I can start with these original word tokens that I had, plus the positional embedding, but then by multiplying it with the attention values, I can basically assign a new representation as I'm generating my output at every time step. So basically, you can think about these decoder blocks. If you look at how this attention mechanism works, since my keys and values are now this input sequence that I have given, what I'm basically doing is I start with I like cats. I have an embedding layer that converts each of these words, which are my tokens, into a representation. But that representation, once that embedding layer is done training, is fixed. The next time I see the word like, I will get the same vector for that. On that, I add in positional information. A vector saying, well, this is word number 1, and this is word number 2, and this is word number 3. Doesn't look exactly like this, but something of the sort, so that I can mix in a bit of positional information as well. My attention layers, what they basically help me to do is they say, well, nice that you have these vectors so far, but since we are now going to generate the next word, I want to play a little bit with these representations, right? I'm not going to directly give this full thing to an MLP for different reasons, also because that wouldn't work, because this thing is of a variable length, right? So also that wouldn't really work. So what I will first do instead is, by having all of the tokens, so query, 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 attend to the other parts in the sequence, I'm calculating attention scores, I'm softmaxing, and I'm multiplying it with these vectors. So basically, these decoder blocks, they change the representations of these vectors. They can basically help to transport information from one token to another token by having them look at each other. And then the typical way how this is typically set up for most language models is that by the end of this process, that you can have this train in such a way where then the representation that you get for your last word is sufficient to pass to an MLP and decode off of what the next word that you want to generate should be. Because the attention mechanism has brought everything that it needs to this last representation to decode off the next word from. And this is something with a fixed size. Right? Now you don't have something variable, now you just have a single vector that you can give to your MLP to predict the next word of. A little bit more about self-attention, but I see that it's almost time, and otherwise I think I would have to rush a little bit. So I suggest that next time we recap from here and we finish up this attention story. See you next week.